generous support. I would like to also thank our partner organization, the GCCD, for their invaluable assistance. China and Germany has a long history of collaboration, especially in the area of academic research and fundamental, let's say, industrial research, industrial collaboration. We share a very rich history in the past. New energy and digital intelligence are the key topics now in the modern society and serving as a vital engine for social progress and sustainable development. This conference has brought together leading experts and scholars from Germany, from China, and from all over the world. So we are here together to explore cutting research and technology application, exchange our ideas, and also spark possible innovation. I firmly believe that through this collaboration, through this close collaboration and in-depth discussion, we can inject new vitality into the academic advancement of and also industrial collaboration between the two countries. So I wish the conference a great success. Thank you so much, and Dankeschön. Yeah.
Thanks to Professor Ding Fei. Next, let's invite Professor Ding Wenjin from GCCD to deliver a speech. 有请留德中国旅德学者化学化工学会理事长丁文进教授致辞。尊敬的徐院士、郭院士、蒋院士 ，Dear Professor Weidenkopf, Dear Professor Chesh, Dear Professor Kunibetti， 尊敬的范院长，邓主席、陈主任以及张强教授、丁辉会长。尊敬的各位教授、学者、专家们、女士们、先生们，大家下午好。我谨代表大会主办单位之一中国旅德学者化学化工学会 GCCD， 向各位参加此次中德新能源与数字化国际学术大会的嘉宾致以最热烈的欢迎。同时，我要感谢所有参会者、组织者，特别是江西省科学院和留德中国物理学者学会等主办单位的鼎力协作，以及承办和协办单位的全力支持。为了实现巴黎气候协议目标，两国都提出了支持工业部门升级和绿色低碳转型的国家发展战略，中国的双碳战略和德国的能源战略。中德两国作为世界第二和第三大经济体以及最主要的工业国家，在工业领域的合作有着悠长的历史以及丰富的成果。比如在化工行业，总部位于德国的国际化工巨头巴斯夫，早在1885年就进入了中国市场，并在19年11月启动了巴斯夫广东一体化基地项目。总投资约100亿欧元，这也是巴斯夫迄今为止在海外最大的投资，也是自新中国成立以来外资企业在中国最大的单个项目投资之一。在最近几年，中国的企业也在积极的出海，在欧洲投资设厂，如宁德时代在德国，一期投资约18亿欧元，建立动力电池工厂，于2023年也正式投产。这样的成功的合作例子很多，而且也将越来越多。尤其在能源转型的大背景下，中德两国的产业升级和绿色低碳转型，所以我们相信中德间的合作将会更加的紧密。基于这个背景，此次大会论坛重点关注新能源与数字化等未来产业 关注江西省制造业重点产业链现代化建设，关注中德间的产学研合作。下面我简单介绍一下我们这个中国旅德学者化学化工学会 GCCD。它成立于36年前，是德国最大的华人学会之一，目前有约600位会员，其中80%以上拥有博士学位或者是在攻读博士学位，10%是教授，其中有10位院士。GCCD 最近在这个和中国很多的这个单位进行合作，承办了，比如说上一年和中国化工学会合作承办了中欧低碳节能论坛，最近刚刚前几天在杭州和中国化工学会西湖大学承办了中德新能源新材料生物制造论坛，其中有5位德国工程院院士和5位中国工程院院士参会。近几年日益严重的气候极端现象已经给人类在地球的生存安全带来了挑战，让全球的能源转型刻不容缓，急需先进、低成本、成熟的新能源技术的支持这个能源转型。个人认为，很多的事物有国界，也可以人为的让有些事物有国界，但引起气候极端问题的温室气体没有国界，人为的也做不到让它有国界，所以我们要实现巴黎协议目标，唯有国际合作这个途径。最后，希望大家在这次大会中，能够增进感情，通过合作一起创新，将实验室成果更快地转化成新型产业，让这个世界更快速地向着绿色、开放、可持续的方向发展。谢谢大家。
Thanks to Professor Ding Wenjin. That's all for the opening ceremony. Next, please move outside for group photo taking together. 开幕式环节到此结束，下面请各位嘉宾移步大门口进行合影留念。合影回来，我们开始我们的精彩的主旨报告。谢谢。 Okay, welcome back. So next session, let's invite our meeting president, Professor Xu Chunbao, to host the next session. 接下来有请大会主席徐春宝院士主持下面阶段环节。有请，掌声有请徐院士。
Okay, distinguished guests, ladies and gentlemen, and also colleagues on site and also online. Good afternoon on site for the guests here, and also good morning for those colleagues online in Germany. First of all, I want to give my sincere thanks to my co-chairs, Professor Guo Liejing and Professor Jiang Jianchun, and also thank the conference organizer, Professor Ding Fei, chairman of GCFD, and Professor Ding Wenjing, chairman of GCCCD, and also vice president of Jiangxi Academy of Science, Professor Fan Ming, for their organization of this very important conference, Sino-German International Conference on New Energy and Digital Intelligence. We want also thank all of you who are attending this conference to introduce your important research, to share your idea about the new direction of research, as well as to establish, foster or enhance the collaboration between the Sino-German researchers in this important field of new energy and digital intelligence. So now let me just start the first session of the plenary talks. As original planned, our first speaker would be Professor Anke Weidenkampf, but Professor Guo has a flight to catch, so Professor Weidenkampf has kindly swapped his talk with Professor Guo's talk. So let me introduce Professor Guo first as our first speaker. Professor Guo is academician of Chinese Academy of Science, academician of Academy of Science for the Developing World. And Professor Guo is also a full professor at Xi'an Jiaotong University. 我现在再用中文隆重介绍一下郭院士。郭烈景院士是中国科学院院士，发展中国家科学院院士，西安交通大学教授。郭院士主要从事动力多项流以及氢能科学技术研究，包括高温、高压、高热负荷、高危险和复杂结构条件下多项流的安全和传控、传质传输、能质传输和转化的理论研究和装备，荣获了首届全国创新争先奖、陕西省教学成果特等奖，主持了煤炭超临界水气化制氢发电多联场技术，并且入选了中国高等学校10大科技成果奖。非常感谢郭院士对我们大会的支持。郭院士也是我们江西人，也是我们江西的骄傲。我们隆重的热烈欢迎郭院士上台讲座。谢谢。
Dear the honor guest from Germany， 尊敬的各位女士、先生、各位领导、各位同仁们，下午好。非常高兴有机会回到家乡，能来大家一起分享一些关于我在能源转化和利用方面的一点结果或者收益。也非常感谢会议的组织者给我这么一个机会，也感谢春宝院士、春宝主席的刚才热情洋溢的介绍。每一次回到江西，都很有感触，由衷的期待江西能够越来越发达，越来越富强昌盛，家乡的父老乡亲能够越来越幸福，也期待有机会通过自己的努力，能支持和帮助江西科技乃至于新质生产力的发展。我是来自一直工作在西安交通大学的能源与动力工程学院。1979年高考从江西遂川考入西安交大，一直在那待着，至今已经有45年。我所从事的工作呢，主要是能源转化和利用。今天给大家汇报关于我们小组在利用生物质及废弃物以超临界水热化学反应气化制氢的相关工作。我将按如下的这个秩序来给大家汇报。首先介绍一下背景。我们知道，热化学反应是人类文明发展的起源。自从人类发现火以来，其实与火相关的都是热化学的过程。那么这个图是关于能源动力转化的，从蒸汽轮机到燃气轮机，热力发电厂在燃气蒸汽联合循环，乃至于今天的能源动力的全产业链，几乎所有的98%、99%都是基于燃烧而构建的体系。所以热化学反应，也就是强烈的热化学反应燃烧，在这个过程中几乎是不可替代。但正是因为这个体系所造成的高温条件下的氧化反应，把一次能源，特别是化石能源的这种不同的多种成分组成的，还有各种无害的或者也无益的这种成分组成的这种能源原料，一把火烧，产生了今天强烈的环境污染和生态破坏。也正是因为这个能源动力的体系排放了巨量的二氧化碳以及其他的温室气体，所以才有今天的全球变暖。这也是我们今天人类所面临的共同的挑战，不管是德国还是中国，亚洲还是欧洲，美洲、 只要是在地球上，这个挑战就必须要去迎接它，而且要解决它。那么中国还存在一个能源的供给安全保障问题。其实我知道，德国也同样面临着能源的安全供给和保障。我们国家的油气资源，70%以上的油是靠进口，45%左右的气也是靠进口。当然，我们还进口很多的煤炭，但煤炭的供给我们基本还是能够自给。在化石能源的这个体系下，我们刚才讲的环境污染和生态破坏是越来越严重的，所以只有从根上去改变，那就要反思我们人类利用能源的基本方式，也就是刚才我们一开头讲的热化学反应，强烈的热化学反应燃烧。而生物质是一个吸收一次的自然资源，包括特别是太阳能以及水汽等，转化成负碳能源，就是它的吸收能源转化的过程中吸收二氧化碳，是个负碳的一个能源资源。它在江西乃至于中国都十分丰富，因为我们的太阳能资源总体是丰富的，水资源相对也是丰富的。我们只是在西部地区的淡水资源不足，但是水资源是丰富的。地球上70%以上的地面都是被水所覆盖，所以如果用好太阳能和水，实际 程，这是我们做了20几年以后，现在形成的很简单的流程。这边是供生物质，在超临界气化反应器里面，把生物质的有效成分碳氢氧气化出来，然后跟水反应，释放叠换出的氢气和二氧化碳，溶解在超临界水中，所以出口是超临界混合工质，而煤炭或者生物质里面的其他的非有效成分是不参加反应，在通过我们的反应器混合，在流态化条件下从底部排出来，以固态的形式液态排插固态的形式以经接近的形式排出来，而我们做出来的是白净的均匀颗粒，跟燃煤发电烧出来的那个渣完全不一样那么上头呢，通过氧氢反应全部释放能量，得到更多的超临界水蒸气去轮机里做功发电。当然刚才讲的这个过程它还可以分离氢一定的温压下把氢分离出来，得到纯氢。一定的做完功以后的二氧化碳是纯二氧化碳分离出来，跟水分离，这个水是可以循环利用的。而且这个反应呢，因为前面第一个反应是还原反应，所以不像燃煤发电加的水是必须是纯净的，要去离子的水。这个反应我可以用含有有机废弃物的废水做原料，跟有机就是生物质有机废弃物或者煤做成浆送进去反应，出来的水做完功以后得到的水是纯净水，所以它这个整个循环又是一个废水处理的高效废水处理的一个循环，所以它的整个过程的能源效率要高得多。刚才说100万千瓦的技术我们核算的，跟对应的燃煤发电超临界发电技术对起来，这个现在是全球最先进的技术，我们也可以高5到5个百分点以上。相对的温压条件降低以后，规模小的提高的效率更高更多，那么可以一步实现二氧化碳的负极，也就不需要现在我们燃煤发电技术包括燃煤的工业炉等在提倡的二氧化碳的捕获过程。这是一个，因为捕获过程同样要高能耗，那么我这个过程是自然普及，这是基本原理。那么我们在这个方面上的一些进展给大家报告一下。就我们做过的这种生物质有各种工业废弃物、城市家庭生活用的垃圾各种有害废弃物，包括核反应堆的，就是核电站里面的一些被照了以后的有机废弃物，这些我们都做过实验。还有石油工业里面生产的各种废液、固液、废固等各种垃圾。那农业生物质、林业生物质的各种废弃物，比如说秸秆、麦穗包果折咱们吃的那个包果的芯，对吧？还有这个树叶果皮还有这个比如说竹子因为江西的竹子很多，对吧？我们都做过相应的实验，都可以在一定的温压范围，就是在超临界水环境中完成它的有效成分的完全气化，生成氢气和二氧化碳。那这些过程中，我们通过加载一定的催化剂是可以降低温压，使得反应更为温和，装备的投入就可以更便宜这个是我们 包括这是做的鸡粪的结果啊，这个而且这种鸡粪是从澳大利亚取回来的，国内的鸡粪、各地的鸡粪都做过，都可以做好啊。澳大利亚的我们也取回来啊，在自己的装置上做过实验。这是猪粪啊，所以各种养殖。清洁能源生产的场地，它不但是比如说我们养猪卖猪肉，对吧？同时，猪排出的垃圾也是可以作为能源物质来利用的，啊，那还有这种是生物质啊，还有我们这个养殖业，就是生物培植啊，有很多这种微生物的废弃的东西，还有包括我们种蘑菇啊等等，不是都在树上长。一段以后，那个东西就废弃了。实际上它是生殖的，啊，有树啊，这个其实它就是碳氢，都是属于碳氢化合物啊。那么都可以作为原料来应用。那这个是有关造纸工业里面的废弃物，我们跟相关的造纸厂以及相关的热电厂结合，通过实验也验证了。完全可以把造纸黑液作为我们的原料，来跟煤炭或者生物质混合做成浆料、进料，来完成生产氢气、发电、供热的过程。那么这个生物质超临界水气化呢，刚才讲起来比较简单，因为超临界水有特殊的物理化学性质。利用这个特殊的物理化学性质，我们能完成生物质原料的第一次转换。那么实际上它的路径和机理还是蛮复杂的，在过程中还有很多反应路径是竞争的，所以我们要通过自己的努力去提高选择性，让反应朝着我们所期待的设定的方向去发展啊，这是相关的一些反应的机理啊。因为时间关系啊，我呢不在这一一的展出，大家可以看反应的 react 啊，但是它也很重要，所以这些反应路径怎么样去控制它，实际上是蛮复杂的。我们通过实验去认识规律，同时还需要我们从机理、从模型上，甚至用 AI 的手段去建立大数据条件下它的模型，来预测整个工艺流程、整个系统的过程。你看，这是生物质原料，好吧，包括热解、气化等等，它的一些竞争的啊，一些反应路径的竞争过程啊。那么我们要借用人为可控的一些手段，包括温压、浓度和反应场的组织，就流场的组织、温场的组织，还有一些定向的一些催化的材料的诱导，形成整个有序的反应。所以我们把这个过程呢也叫能源有序转化，就使得这个过程既得到我们所希望的产品，又要使到这个过程里面的不可逆的能源损失、能量损失是最小的。那这是一些实验结果，我就不一一在这展啊，就交流要讲。那么这个是关于啊部分的模型和动力学模型的啊一些预报的一些结果。你看，这是啊预热反应，你看，比如说这个反应器里，第一部分是主反应啊，这个是预热区，这个呢就是反应后往上走的一个净化分离区啊。所以在反应的液叫 slurry， 就是我们做成浆啊，这个浆的喷注和分配就非常重要 它当然这个图都是示意性的，这里头有很多螺号包括喷嘴的大小、喷嘴的角度、喷嘴的里头的流体的流速、温压的控制等等这个都是一个比较复杂的过程。我们已经建立相应的体系，有相应的软件包，还有相应的专利这些都是反映的路径那么碳氢气体生成的各种路径之间的竞争性，您看，如果反应不完全，它是有可能生成一氧化碳、甲烷等等。但我们的目标产品是氢气二氧化碳。后来我们通过努力呢，在研究过程中呢，也根据化工过程的需求，我们也可以定向只产一氧化碳或者产甲烷，但它的产率就要根据不同的原料、不同的反应环境和条件要进行调整。第四个过程呢，我想汇报一下我们这个超临界水反应过程的调节那么这个调控刚才讲的，一个是流体力学，你看室内的这个浆液呢，实际上那里生物质还是颗粒型的，所以 particle 在里头的规律、流动、反应的规律，因为它都在 particle 的界面上完成的，也是非常非常重要的科学问题和核心关键技术。所以这里展示的，实际上里头就是典型的 multi-phase flow， 有多项流动、传热传直和化学反应耦合的过程那么跟燃烧一样，它还是典型的热化学过程，但是这个反应呢，跟燃烧不同的是，它的温度要低得多。我们各种各样的原料做过，完全气化的条件在670度以下基本都能完成，最高也不会超过700度。而我们知道燃烧反应最低也在800-900度以上，一般的反应都在1500-1600度。所以这个温度下耐这么高的温度，对于材料而言要求就更为苛刻。相对而言，我们这个过程就因为温度条件比较低，所以我们把它叫温和的反应，对材料和装备本身的要求就比较低。这是相关的一些基本的过程，从关键问题到求解到方法发展，系统的构建这些整个的体系，我们都已经现在正在做一些示范工作那么比如说这是超临界的流行的分布特性，这个呢是扩散定律比如说酶的在这个临界转换区的一些规律，我们可以得到一系列的这个流动和传热的基本规律和它的计算方法那么这个是一些流态的演示这个比如说这一个煤炭颗粒，在这个过程中气化过程中的它的不断的气化、不断的缩小、群空的一个过程实际上这个小颗粒内部还有很多空隙，是微流道的空隙。这个过程为什么超临界态的水那个反应这么好？其实这是就是不管是煤炭还是有机废弃物的这种颗粒，它的多孔的介质给超临界态的氢链已经断开的超临界水呢一种强化的反应的一个这个场景这是这个能量转化的过程最佳的匹配的一些条件您看到这个竖式，比如这是展示了一个立管式的反应器，它的在过程中的一些温压的分布这个是不可逆损失的，在反应器各段它不可逆损失产生的 大小和它的分布啊。那么这是我们在相关的地方，比如右边这个图啊，是我们在学校里面建的一个5单元的5个反应器并联的一套装置。这个装置已经运行2万多个小时，把我们的原理都已经验证并且可以实现就是连续生产工艺。左边这个上面这个图呢，是在宁夏盐池县的太阳山上，利用太阳能的供热来提供气化反应的源啊，那么实现了整个生物质气化的一个过程。这也是国家原来863项目支持下做的第一个示范工程。那么所有的气化效果，刚才我们已经讲过。您看现在这个技术呢，我们在这一块啊，它中温反应，所有的其他的气化，比如说煤气化、传统的煤气化，全球各类的气化炉子工作的温压都是比较高的，尤其是温度高得多啊。压力低了以后呢，气化效果就不好，所以大家都在做高压、高温下的啊，尽可能的把压力提高。但是传统的气化过程，它的气化效果比较低，气化的流动气化的这个气化率比较低，超零这是相关的一个传统气化的一些对比价格的对比，比如说制氢，我们可以这个技术下，在100万千瓦做基础对应的，它的氢的成本可以降到1标方6毛多钱这是相关的示范的工程，我刚才已经讲了。这是我们在佛山市做的5万千瓦发电机组对应的，并且是每小时产1万标方氢的这个装置，现在已经设计完了，正在生产和组织施工过程中。这是相关的结果我们知道这个11月8号我们国家全国人大常委会正式通过了新的能源法，是把氢能正式纳入能源法律，作为能源来管理的。此前我们都知道，中国是把氢作为危化品来对待，是不安全、危险，甚至会爆炸。还有人联想的氢能跟氢弹联系起来，非常危险。其实不是那么回事，氢很happy，这是我想给大家那么联合国包括 COP29 11月13号同样通过了大会议程关于全球的氢能助力气候行动。我想以生物质为源的、以水为基的热化学反应，特别是气化制氢，在这个里头会起到极为重要的作用。我想在这个场合也呼吁江西省的政府、企业加速 focus 聚焦氢能技术和产业，推动氢能技术及产业在江西大地早日生根发芽，赶超甚至走到世界的氢能产业新质生产力发展的引领地位上去。谢谢大家。
因为时间关系，我们就不提问了。但是我可以很骄傲的跟大家说一下，我们国院式的超临界水制氢应该世界上应该是 No.1， 就没有人能超过这个的，就做了这么大规模，而且理论实践都已经做得很前沿。所以说，再次感谢郭老师给我们做了这个报告。 Okay, our next talk will be by Professor Joanna Relio Kunibuti. And Professor Kunibuti will be giving a talk online. I'm not sure if Professor Kunibuti is online or not.
Yes, I am.
Oh, yes. Okay, thank you. Let me give a brief introduction on you. So Professor Kunibuti is a fellow of German Academy of Engineering, chair professor of material science and nanotechnology at Justin University of Technology, fellow of American Physical Society and a rotary of GCCD. Kunibuti 教授2027年以来一直担任德累斯顿工业大学材料科学纳米技术讲席教授，并且是德累斯顿大学智能材料中心的创始主任。Now, Professor Kunibuti will give a talk on the machine learning for molecular sensing. Professor Kunibuti, now the time is yours. Please share your screen and we can start. Thank you. 大家欢迎。
Yes, thank you. Thank you very much for this amazing opportunity to present something here. Unfortunately, only remotely. Before starting, I would like to mention the many friends that are there in Jiangxi, so anche Weidenkauf, Ehrenfried Czesch, also from Dresden, Benjin Ding, Fei Ding, my good friend Mariana, Bergoy, Carlos, and Shirong, friends and collaborators. I don't know if you can see my monitor. Yes, I guess so, right? Sure. Okay, here we are. We have been also hit by the AI wave already 10 years ago, and what I want to tell you in these minutes are how this impacted nanomaterials and the digitization of the missing sense. So thanks again also for the generous introduction, Mr. Chairman. Well, we speak about China and German friendship, so let me just remind that we are in the east of Germany, in a very central region of Germany. It is a stronghold for materials research with 2,000 scientists only in the field of materials research, and an annual budget that this was 3 years ago, is already higher, for research of 300 million. We are no doubt, as university, at top 20 worldwide in material science, but if we aggregate with the Max Planck, Fraunhofer, Helmholtz, and the Leibniz Institute, actually here there is the Fraunhofer Institute that Professor Czesch used to direct, we are a top 3 location worldwide. Surely the highest density on planet Earth of transmission electron microscope, like friends from FEI and JEOL told me. Well, life is cool, and actually in this case warm and nice, especially in the summer month, and you are all invited, many of you have been already experienced Dresden, to visit us. I want to start with a little bit philosophical. You know, I show a sky over Dresden, and this is a molecule. Typically, when I'm in person, I tend to ask questions, etc., but it is difficult on a distance. But you might imagine this linear molecule, cigar-like, is a CO2 molecule. If you make 10 billion times smaller, it is what it is, a CO2 molecule. Probably with this huge screen in China, you have to make it even a little bit, probably 100 billion times smaller. Why I tell you about that? Because removing this molecule from the atmosphere is one of the really achievement of mankind. I mean, we need to reach this goal. Actually, the goal is already accomplished. That's why we are in a fantastic equilibrium on planet Earth, and this is done by our trees, our forests, and I think to the beautiful scenery in Germany and also in China. The point is that the rate in which we re-emit this former CO2, this wood is basically former CO2 from the atmosphere. but the rate in which we emit in the atmosphere is much higher than what these objects can do. That's why it is really searched like a holy grail, a way to catalyze back from the atmosphere this CO2 in some material. And that's still an open topic. Probably there will be the first Chinese Nobel Prize for CO2 capture in an efficient way, because we have many inefficient way to capturing it, and wood still is among the most efficient. But let me tell you a story which is dating back of more than 100 years ago. Is the story of these two gentlemen, Fritz Haber, who was the scientist finding the catalyst after searching and searching and searching, showing that really success is just standing up one more time, and Karl Bosch, the company guy that eventually scale up the process in the BASF at that time. Actually, he got a Nobel Prize in the end of the 30s also on using the same process to produce synthetic fuel. And I call this natural intelligence to it as third person of the pronouns, so matter, the Latin id. So something is not IT, but it. So, and I to it is an amazing story. If you have the chance to, now that probably the spring holidays are approaching, and in Europe earlier the Christmas, to read CCD, Beijing is here. I was really humbled by getting this prize as best supervisor of Chinese students in 2023. But why I tell you this? I tell you this because I had the opportunity to have a Bilibili interview. So if you can scan this QR code, I'm telling here a few words about why studying in Dresden is really one of the best places on planet Earth to conjugate material science and electronics. And then you can go back to China and have a lot of exchange with China, but please also experience this amazing part of the world. I don't know, that's, the audio is in English, or my English, but everything is with subtitles in China. And it's quite funny because I don't go with the chemistry the hard way, but we speak about living there, how is life, and so on. Okay, that's all, really very much to tell you, and I thank you deeply for giving me this opportunity. I would have loved to be with you, but I had the Excellence Initiative yesterday to defend in Bonn, and I am on Sunday I had already a commitment taken in Jeddah. So this time, unfortunately, I cannot join the face-to-face meeting and the amazing friendship of Chinese colleagues and the fantastic food that always I experience in China. So thank you very much. Don't hesitate to send me a WeChat note. Would like to do something with us, if you look for a job, if you have an idea. My students open my eyes on the world of WeChat, and now at least every second day I have a look also on that. Thank you very much, and sorry if I was a little bit longer than planned. I'm kidding.
Okay, thank you, Professor Kunin-Berti. So very inspiring talk. So I think we will leave the time for future questions because we will catch the schedule. So thanks again. I hope to invite you. We will invite you to China to communicate with our colleague here on site in the near future. Thanks again.
Yes.
Yeah.
Thank you. Deeply gratitude. Thank you very much. All the many greetings to all the friends.
Thank you. Yeah. So now we are moved to our third talk. So Professor Markus Roser. So Markus, are you online already?
Yes, I am. Hello, can you hear me?
Very good. So I'm very glad to introduce my friend, Professor Markus Rose. Professor Rose is a full professor of chemical technology at the Technical University of Darmstadt. Regretfully, Professor Rose could not join us online, on site, as you know. So he will give a talk online about the ammonia as a sustainable hydrogen carrier, perspectives of synthesis and the cracking technologies. Now, Professor Rose, the time is yours. Please.
Yeah, thank you very much. I'm deeply honored for the invitation, Charles. Thank you especially for inviting me to this conference. I'm deeply sad that I could not be there due to other obligations till yesterday late in the evening, and will continue tomorrow. But I would like to share some insights with you on a very important topic from my point of view. Now we turn totally gears, topic-wise, go towards chemistry, catalysis, chemical engineering especially. And I would like to look a little bit backwards, but especially forwards on perspectives of synthesis of ammonia for specific types of usage and cracking technologies specifically. But let me start with a short promotional slot on where I come from and where we work and what our surrounding looks like. And if you are interested in more details, you should talk to Charles Chu, because he visited us this summer. It was a great time we had together here in Darmstadt, and I'm hoping really much he will come back as well. So Darmstadt is not so well known because it's a rather small city, but quite centrally located in Germany, in the Frankfurt Rhine-Main region. The whole Rhine-Main region has about 5.5 million residents. That's not much compared to mega cities in China, especially, I know, but still we have some other things which are quite impressive. Let me briefly introduce our university. The Technical University of Darmstadt is quite old already, from the 1830s. so nearly 200 years old. We have roughly 25,000 students, and the city only has 155,000 inhabitants, so it's quite a high ratio of students, and it's a nice feeling living in the city here. And for German university, it's quite international, with about 25% of master students, and we belong to the 9 leading universities of technology in Germany. Outside the university in Darmstadt, we have some special entities like the European Space Operations Center, which we are very proud of, from the European Space Agency, is located in Darmstadt. So many satellite missions are controlled from this place. We have, for example, the GSI Helmholtz Center for Heavy Ion Research, also quite well known. There are some elements were discovered actually from the periodic table. For example, the Darmstadium. So this actually was discovered here in the vicinity of our city. And there's more research going on in institutions like Fraunhofer Institutes. We have several of those. And outside Darmstadt, and then in the Frankfurt and Mainz, in the Rhine-Main area, there's a lot of other research institutions as well. But there's also things we can do here outside of science. Darmstadt has, and its surroundings especially, there's a lot of arts, culture, and nature. I just leave you with these impressions here. And the University of Darmstadt and Darmstadt itself was already promoted like over 100 years ago by Albert Einstein, who said, in my opinion, you definitely ought to go to Darmstadt. They have a very good polytechnic school there. So words of recommendation from a world-renowned person. I would like to start with, because I want to show you some things, more general, but also some work we do in our group. And this is not what I did, but a very good group of people you can see here with a rather recent group photo, which is doing the work. And we mainly work in the phase of reaction engineering, a little bit separation, process design, developing new catalysts and catalytic processes. This is what we aim for, and on the bottom you can see all these logos of our funders and collaborators from industry. And I want to point out 2 projects here related to the ammonia topic, which is the priority program Nitro Conversion, where we are involved in, and I will show you a little bit in the second part of my talk about that. And the other project is funded by the Fritz and Margot Faudi Stiftung, which is funding part of our ammonia cracking work. I will also briefly mention towards the end. So what I want to talk about in the following, and I'm not sure if I can get you back in your time schedule, but I do my best. So first I want to introduce ammonia as a very important molecule, very important compound for energy storage, chemical energy storage. Then I want to briefly look back, but also forwards in the Haber-Bosch process, because there is interesting developments on improving that technology. And then I want to point out alternative synthesis options, and as well the ammonia cracking, because we have a specific goal. We want to obtain the hydrogen we can store in the ammonia. Let me start chemically stored energy. And then you need to somehow replace central and decentral hydrogen production, because currently the largest share, and I'll show you numbers in a minute, is coming from steam reforming of natural gas especially. So the ideal goal is to have later on, and hopefully 1 or 2 decades, a significant share of renewable energy that can go into water electrolysis, produce hydrogen, which is then later on used for different sectors, which are the main emitters of CO2 and which have the main industrial energy requirement: the steel industry, chemical industry, refinery applications, many more. But the hydrogen itself poses some severe challenges in terms of logistics. So storage and transport are doable technologically, but there's more efficient ways of doing it than storing and transporting pure hydrogen. And this is where ammonia comes into play here. Ammonia synthesis is well known on a world scale by the Haber-Bosch process, and very large, huge centralized mega plants basically. And this is not so much in the focus in the past. You also can crack the ammonia and gain again the hydrogen by cracking or and that in a centralized or more decentralized manner. And this is the technology I want to focus on today. So hydrogen storage systems, why specifically ammonia and not other storage systems? This is nicely demonstrated by this graph here on the right side, where we see the volumetric capacity versus the gravimetric capacity. And if you look into typical storage options, compressed or liquefied hydrogen, we see that we have rather low capacities, volumetric as well as gravimetric. Then there's opportunities like adsorptive storage in porous materials, for example, zeolites, MOFs, carbons, which have been discussed for the last, let's say, 2 decades especially, but there is one example, MOF 210, which has a high gravimetric but a not so high volumetric capacity. And then there we have a huge bunch of options as chemists, can form hydrides. They have large volumetric capacities but low gravimetric ones, and they have a big disadvantage. They are typically solids where the hydrogen needs to somehow go into, and then we have severe kinetic limitations. Hydrocarbons are an option to store hydrogen under the buzzword power-to-X technologies, where you can produce highly reduced hydrocarbons, which you then can use to reform the hydrogen. Liquid organic hydrogen carriers are around for some years now, which are probably a viable technology in the future, but only for rather small scale or medium-sized scale hydrogen applications, not for global hydrogen market. And there, from my point of view, ammonia plays the biggest role. Here you can see we have a very high gravimetric and a very high volumetric capacity. And the big advantage is if you remove the hydrogen and use it, you just have the nitrogen. The nitrogen is 80% of our air. So nitrogen is everywhere. You can get it, you can obtain it, convert it. And if you crack the ammonia, you can release the nitrogen again. So that is the most convenient storage molecule from my point of view. Another thing is associated to that is the costs. So the ammonia, of course, is a liquid gas at ambient temperature. You have liquid ammonia at about 8 bar of pressure. So it's easy to store and to transport also in large amounts. The technologies are available. And if you look in this graph here, it's the price in US dollars per kilogram of hydrogen for the transport plotted via the distance. And of course, pipeline transport of hydrogen becomes linearly more expensive with the length because you need the pipeline infrastructure. If you use not pipelines, but for example, ships for global transport, and compare here different technologies, liquid or pressurized hydrogen, ammonia, and the LOHCs, which are still under development, ammonia is really among the cheapest transportation options for a world market. So this is the driving force behind these ammonia technologies. And I want to point out some large-scale ammonia projects that where there was a significantly rising interest in the last years in Europe, in Germany especially, and there is some partnerships with several other countries in the world going on, where the share of renewables will allow the production of green ammonia, hopefully in a few years only, and there's partnerships to bring hydrogen via ammonia as storage medium then to Central Europe. There's, for example, partnerships of Germany with Norway, companies VNG and Yara. They are currently planning a huge ammonia cracker in Rostock, a harbor city at the Baltic Sea, where there's already quite an impressive ammonia infrastructure, so that you can see on the right side in the picture without any details here. And there's another partnership, Germany, Canada, with Uniper and E.ON, a German energy company. They are also going for ammonia apparently as a storage molecule to get renewable energy, renewable hydrogen across the Atlantic Ocean. And there's a lot of know-how here in Germany, especially on the technology development. Companies like ThyssenKrupp Nucera, ThyssenKrupp Uhde, who are experts in electrolysis, ammonia synthesis and cracking technologies. Linde Engineering, Saudi Aramco, building ammonia crackers. Air Liquide, who is an expert company on the development of steam methane reforming technologies, which is not that different in general compared to ammonia cracking. And they are building first crackers already, for example, in Belgium and Antwerp. So this is technology that is really currently ramped up and built on an industrial scale. BASF, of course, with an ammonia synthesis worldwide, have a Bosch process which they are running, and they also have, for example, steam crackers as a fundamental technology for the chemical industry, and they So that's the first part. Let's briefly look into the Haber-Bosch process, and I hope I can also tell you some new things here. Actually, this year I looked it up. The Haber-Bosch process turned 111 years old. Nice number, because in 1913 the first large-scale process started operation in Ludwigshafen. And as mentioned by my previous speaker, Haber and Bosch invented the process. Haber was the one dealing with the chemistry, the catalysis. He and his co-worker Adil Mittasch developed the catalyst. And Bosch not only did to deal with, but Bosch also made a very specific invention I want to mention in about 2 slides. Let's have a briefly look on what we have to deal with. Repeating technology, because many people nowadays claim they have the new catalyst for alternative ammonia production under mild conditions, but we still have to kind of use the Haber-Bosch process as a benchmark here. So if we start classically from methane, from natural gas, we need first typically a hydrodesulfurization step. It's not shown here. 1 catalytic step. Then typically steam methane reforming in 2 steps, a primary and a secondary reformer shown here and here. You produce a lot of syngas basically. Then 2-stage CO conversion, so water gas shift reaction, high temperature and low temperature, typically coupled. Then you have a CO2 scrubber, so you have an absorption process to remove the CO2 that you form, and then you have trace amounts of CO2 and CO in the system, and you need to get rid of those because they are catalyst poisons for the Haber-Bosch catalyst. So what you do, you have another reactor, also not shown in this graph here, that would be suited somewhere here. You have a methanation to produce like 1% of methane as an inert gas, which can go through the Haber-Bosch reaction itself. Then you have huge compressors because you need the very harsh conditions, about 300 bars of pressure to run the process. Then you have the actual Haber-Bosch reactor, the ammonia synthesis, separation by condensation. And as you by one run through the reactor only convert about 15% or have yields of 15 to 20% of ammonia. You have to condense them, separate them, and you have a huge amount of gas recycle which need to be compressed again. And actually, as the Haber-Bosch process itself is a strongly exothermic reaction, you produce a lot of heat. But often it's claimed that the Haber-Bosch process is a very energy-intensive process. Why is that? It's easy. You need a lot of energy for the endothermic hydrogen production by the steam methane reforming, and you need a lot of electrical energy for the compressors because of these huge pressures you need to build up, and because of this huge gas cycle. This is what makes up the high energy consumption of the Haber-Bosch process in general. We need to consider thermodynamics for the reaction, and I just want to briefly show you here some equilibrium data. So this is the ammonia yield, or the amount of ammonia you can obtain at specific pressures and at specific temperatures. And because we have a strongly exothermic reaction and we convert 4 gas molecules into 2, equilibrium tells us, or thermodynamics tell us, that we have decreasing yields with increasing temperature and decreasing yields at low pressures. So ideally, we would have a low temperature process at high pressures. That doesn't work because at low temperatures, Arrhenius does not apply, or does apply, but according to Arrhenius, the kinetics is very slow. So a low temperature process is often not feasible. That's why we need at least a temperature of about 400 to 500 degrees C, and operating pressures to be in a suitable range of ammonia formation between, let's say, 15, 20, 30% of 250 to 350 bars. That's the limitation you always have to consider. Then you have the kinetic side, the catalyst side. Typically, industrially, it's a magnetite catalyst that is used as a bulk catalyst, so several promoters. There's a lot of secrets from the industry, what other compounds are in there. And it's known that under reaction conditions, you form a highly dispersed alpha iron phase as reactive phase. And this is actually what there was a Nobel Prize for in 2007, awarded to Gerhard Ertl from the Fritz Haber Institute, who basically investigated the mechanism and proved that the mechanism is really based on this dissociation, the activation and dissociation of nitrogen, of hydrogen, then the addition of the hydrogen to the ammonia, all on the surface as a surface mechanism, and then finally the desorption of the ammonia. So that's the background, and that's the benchmark we have to comply with when we compare other technologies. And the first reactors that were built from the process 111 years ago, they used these type of reactors. And here is now the specific engineering, the genius of engineering of Carl Bosch, who solved a very specific problem. So the typical problem was that these harsh conditions had one problem, that the steel they used to build the reactors, they contained a certain amount of carbon for the very high strength. But the harsh conditions, the hydrogen diffused into the steel, dissolved the carbon, hydrogenated the carbon, methane diffused through, and the steel got brittle. And while the steel got brittle, the first reactors in development process, they just exploded at a certain point. And Carl Bosch solved the problem by using a carbon-free or carbon-poor steel as an inner tube, which is not strong enough to maintain the high pressures. And he had a second shell of a high carbon-containing steel as an outer, very rigid and solid shell. And he inserted the so-called Bosch holes. If you look here in this picture, you can see these tiny holes. So the outer shell had holes to release a tiny amount of hydrogen that diffuses through the inner layer, and then it could go outside. But he had this mix, this composite reactor, basically of a not so strong, but dense enough and pressure containing inner layer, and this outer layer which gave the reactor its total strength. So that was the beginning, and that was the genius engineering of Carl Bosch. And nowadays these plants look like that. This is a typical ammonia reactor here, one of the BASF in Ludwigshafen, although they shut them down due to the drastically increased gas prices. Typically we have a multi-layer fixed bed reactor where the conversion is happening for all the infrastructure, of course. And these plants convert up to 2,000 tons or produce up to 2,000 tons of ammonia per day. and you have a few tons, range of 20 to 50 tons of catalyst in this reactor, you can calculate productivities. And I will come back to that at the end of my talk, because there is a big issue with new technologies so far. So people are still working on improving the Haber-Bosch process. There's a lot of process intensification going on, research going on, and I just want to point out one specific example here. So conventionally, I mentioned it, we have condensing of the ammonia, have to recycle, because a lot of ammonia is not formed in one pass. It's just 15 to 20%. And there's options for so-called sorption enhanced reactor here, shown very, very simplified, to avoid ideally this huge gas recycle. And there's process simulations that have shown that you can actually save a lot of energy with such an option. So this is the specific energy demand in gigajoule per ton ammonia produced, the conventional process, which typically needs most of its energy for syngas compression, as I mentioned before. If you decrease the pressure, you have lower compression. If you even further decrease the pressure, you barely have any syngas compression, which is a problem anymore, but you have the huge recycle gas compression and a huge amount of energy for refrigeration compression, because you produce so tiny amounts of ammonia at 20 bars that the whole separation becomes tedious and a lot of the energy goes into this cycle. If you have a sorptive separation process at low pressures, you also need quite some energy for the sorptive separation itself, in this case a temperature swing adsorption, and recycle gas compression. But if you combine all that into an in situ separation process, so shifting the equilibrium by adsorbing the formed ammonia and not having a significant gas recycle, you need, of course, energy for the sorptive separation, but otherwise you have a low pressure process, which could overall have significantly lower energy needs compared to the very classical Haber-Bosch process. So that's just one of the innovations out there, ready to use, basically. Next generations of ammonia, if we first stay with the Haber-Bosch process, of course, we need the hydrogen from a different source than the methane. We can do water, or we have to do water electrolysis for that, coming from renewable energy, but then we need the nitrogen from somewhere, also from the air, but then we need specifically a separation unit that separates the nitrogen out of the air. Then we can do more or less classical ammonia synthesis and deal with this whole ammonia-based hydrogen economy in a quite efficient manner. And that's often considered the second generation of ammonia. They are doing more or less classical Haber-Bosch synthesis, but with renewable hydrogen. And there's predictions showing, so this is the increase of ammonia over time for a certain scenario of ammonia-based hydrogen economy. The second generation is about to get started, basically, and there will be a third generation, and this will be the aim we have to strive for, to combine the synthesis under much milder conditions, if we can manage with the thermodynamics and the kinetics, with the water splitting. Combine nitrogen activation, water splitting, and then directly produce the ammonia without the need for this very harsh Haber-Bosch process or its modified versions. So that's the outlook. Let me show you which other alternative options are out there. And here I want to go a little bit more in what we do and did in the past. And I want to highlight here two technologies. One is mechanochemical ammonia synthesis as an interesting option, I would say, and then photocatalysis specifically. Some years back, we had a collaboration with a group of Carsten Sievers at Georgia Tech in Atlanta in the US. From this collaboration, this paper here was the result I show you, and they started with mechanocatalysis and figured out more or less by accident that there's some materials like titania, when they started with, that can activate nitrogen and form titanium nitrides. Later on, they figured out, we also can form titanium nitrides by ball milling, so energy input by mechanical forces, starting from a titanium powder. And then we can increase the nitrogen content of this titanium nitride. And if you then add hydrogen, and we can do this at once, we always form ammonia. This is what we found, what they investigated in detail. Our part here was looking into the fact if materials like these titanium nitrides also show thermal catalytic activity, like in the sense of a Haber-Bosch process. So thermal catalysis under hydrogen and nitrogen, activating both species. And we did that, and I just want to point out that one diagram here, that's the ammonia formation rate in the temperature ramp, starting at about 600 degrees C, going up to 900 degrees C. So for the thermal catalysis, we need high temperatures, but many materials are active for the ammonia formation. Actually, what you can see here, without a catalyst, even at high temperatures of about 800 degrees C, even without a catalyst, sooner or later you start to form some ammonia. And although the activity is very low here, it is there. If we use titanium nitride, you can see that there's specifically a higher formation rate that we observe. So there is thermal catalysis definitely going on. And you might know, if you have worked with mechanocatalysis, mechanochemistry before, there's a lot of theories about the energy introduction into the system, if it's just the mechanical energy input by the collisions, if there's hotspots forming. The overall temperature does not rise that drastically, maybe to about 100 or 150 degrees C, but hotspots you might have, which might have very locally, with tiny spatial resolution, much higher temperatures. So this is just an outlook. There's some other groups worldwide working on this mechanocatalytic ammonia synthesis. I'm not sure if that is really the best option to scale it up on a large scale, because ball milling, of course, milling technologies can be scaled up. But as soon as you have moving parts, you have losses. Your material might get lost over time. So leaching is an option, or is a problem probably. I'm not fully convinced if mechanocatalysis might be the best option here. Let's talk about photocatalysis. So what do we do there? We need photocatalytically active materials that somehow absorb light or radiation of a certain wavelength, depending on the band gap. Then you can activate some electrons here, form some holes, some electron hole pairs, while the electrons can then do reduction reactions like the nitrogen reduction. And ideally forming with protons the ammonia. That's the ideal case. And you need a second reaction, an oxidation reaction at the holes here. For example, the oxidation of water forming oxygen. Or other side reactions that somehow deal with these formed holes. You cannot just use one side, you need always to consider both sides. And that's a big trouble, often neglected in photocatalysis, actually. So the nitrogen reduction occurs by these two reactions, the oxidation reaction, the reduction reaction, and overall you could convert, and you can convert nitrogen with water to ammonia and oxygen, or some other oxidized products. We were wondering, is there a role, what is the role of molecular hydrogen? So, because water splitting is a competing reaction here. Water splitting to oxygen or other oxidized products and hydrogen, molecular hydrogen. And the question is if such photocatalysts would be also able to activate molecular hydrogen, because we see that it's formed as a side reaction. It's a competing side reaction here on the reduction side. And that's a critical thing that is not often considered much in detail. So competing reactions is a big issue. And the other thing we ask ourselves, and this is part of our project in this priority program, nitro conversion, is what is actually the influence of pressure and temperature in photocatalysis? Because if you look at literature, people developing photocatalysts, they often screen at ambient conditions. 1 atmosphere of pressure, 25 to 30 lab temperature maybe. And often the temperature is not even mentioned, or it's not mentioned that a high power light source might put in so much energy to your system that your temperature rises. And we are wondering, because Arrhenius should still apply, so we should see an effect of at least the temperature on reaction rates. And this is what we are going to investigate, or what we are investigating in this priority program. Very briefly here, what materials do we work with? We choose bismuth oxy halides as model materials because I think there's a lot of potential in, for two reasons. So it has been shown that they are quite active photocatalysts, but they allow a very nice band gap tuning, and that's interesting for the photocatalysis. So here shown, for example, bismuth oxy bromide iodide mixture, and you can vary the amounts of the anions, and then you can really see optically that the band gap is changing, in this case in the visual range here as well, the chloride iodide. And here you go more in the UV range. Then you have white samples, of course, but still band gap tuning is nicely possible. That's an ideal model system for photocatalysis. Here just some results from our work. So we work with such a high pressure reactor, which is very often not used in photocatalysis. That allows us to work at up to 200 bars of pressure and high temperatures to 300 degrees C. So really can investigate the influence of these conditions on the photocatalysis. We have this lamp going through, shining through a glass window, a quartz glass window here on the site. And this is a tiny diagram with some result points, ammonia concentrations versus time. You see that there's ammonia formation, but look at the concentrations. It's micromolar amounts overall. And there seems to be kind of a limitation over time in a closed system, in a batch system. And this is something you will find in all the literature. You always end up in micromolar concentration ranges. And somehow there is limitations, severe limitations that limit the production coming into micromolar or molar concentrations. So if you look at the total ammonia concentrations that are formed based on the amount of catalyst in a suitable time scale, the rates are way lower. I'll show you a number at the end, way lower than compared to classical Haber-Bosch. And not only a little bit, but orders of magnitude lower. And there is big limitations, and we try to look for these. I do not have a final answer yet. Very briefly, as the time is flying by, and I think I also overdue, on ammonia cracking. You need to release the hydrogen. The cracking technology is, as I mentioned, currently already rolled out, planned on a large scale. Plants are built. So the catalysis is not that difficult, I would say, but we have to consider also some things. So we have the backwards reaction, which is highly endothermic. So we need to put reaction enthalpy into the system. We want to have a high conversion, ideally, at a high pressure and a low temperature. Because what we need is, we want to minimize the required energy, except the need to compress a lot of electrical energy. But we have this thermodynamic limitation. Here's the equilibrium curves shown for the conversion of ammonia in the cracking at different temperatures and different pressures. And you see at low pressure, dark blue curve here, you could go down to very low temperatures for cracking, and you could obtain nearly full cracking at 400 to 500 degrees C. But as soon as you increase the pressure, the limitation kicks in, and you can only crack part of the ammonia. For example, here close at 500 degrees C, up to 90%. You would always have residual ammonia amounts in your cracked gas. So this is the limitation you have to deal with and you have to consider when you screen catalysts, that you are always keep away from the thermodynamic limitation. So the big challenge here is to find catalysts that can, at a certain given pressure, crack the ammonia with high activities to go to the lowest temperatures possible, and ideally you would achieve temperatures below 500 degrees C. Just in terms for the efficiency of the heat integration you can do afterwards. If you look into literature, and I go briefly about that, you always find these volcano plots, and the message I want to give to you is a good ammonia synthesis catalyst is not necessarily a good ammonia cracking catalyst, because you need to activate different molecules. The synthesis catalyst needs to activate the nitrogen triple bond. The cracking catalyst needs to activate nitrogen-hydrogen single bonds. And you can see here the iron, for example, is one of the best synthesis catalysts, while it's not the case for the cracking. So the typical metal that is now in the focus for cracking is nickel. Nickel actually, because it's also cheap and easy to produce in large amounts compared to ruthenium. So the amounts we need, nickel would be the best choice from the current point of view. I mentioned this, so you see here the activity a ton relative to ruthenium. Nickel is far above, on a logarithmic scale, far above the iron in the cracking activity. And what's also known is that highly dispersed nickel, so very small particle sizes, give you very high rates, very high TOFs. Very briefly on what we did, so we focused on a system of nickel supported on alumina, and we figured out a synthesis route, a very specific one, which was kind of a finding by accident, because in ammonia TPD for characterization, a PhD student of mine didn't see any ammonia anymore, while there should be ammonia dissolved at a certain temperature. And after a long search for the possible error, we figured out the ammonia is cracked. It just vanishes. And that was the beginning when we started working on the ammonia cracking. So we have highly loaded nickel catalysts prepared by a very specific route. I will not go into detail here. And what I want to show you is, this is conversion curves, conversions over temperatures. And you see that one of our catalysts here, the blue curve, has at 450 degrees C the highest conversions compared to all the others. There's also a commercial ruthenium catalyst, a commercial nickel catalyst. Our catalysts under these identical lab conditions, still way too idealized, but there is significantly higher activity possible compared to some conventional catalysts. Okay, let me briefly summarize and give you some take-home messages. So I've shown you why ammonia is such an interesting molecule nowadays, despite the huge production amounts for the industry and especially the food production in the end. Yeah, we need the ammonia also for food production, of course. Our wash process, where it needs to develop in the next decades, and the alternative synthesis options by photo and mechanocatalysis, as well as the cracking. What's the key take-home messages? Always consider the influence of temperature and pressure. Never do experiments and just assume, we have ambient conditions, that's the ideal case. You always should investigate how these very important physical parameters affect your performance. And also consider the thermodynamics, the limitations that typically occur in such equilibrium reactions, and then consider the kinetics, investigate the kinetics, how perform over time. The reliability of your experiments need to be taken into account. Often there is low rates and low concentrations within a certain signal-to-noise ratio. You need to be very careful about that. Reproducibility from catalyst preparation and the catalytic experiments needs to be taken into account. And now comes the most important part, and this relies specifically to mechano and photocatalysis, also electrocatalysis. Aim for high productivities. For a typical industrial reaction, you need to come into a range of kilogram product per kilogram catalyst per hour. When you look in literature for photocatalysis, for example, you are in the order of magnitude 10 to the power of -5. Too slow compared to the thermal catalysis. And this needs to be addressed. These limitations needs to be identified. And then we can really talk about an innovation. And I would like to finish with a quote from a US business professor some decades ago. He said, the electric light did not come from the continuous improvement of candles. And I think this nicely demonstrates the need for disruptive innovations. Just making tiny improvements and optimizations is not enough, but we need to understand what we do. Not just do something if we know how we do it, why we do it. That's the better way. And with that, I really thank you for your attention. Thanks again for the invitation. And I think there's no time for questions anymore, but thank you.
Thank you, Marcus. So because time constraint, so we don't have a question for you now. I'm looking forward to visiting your group next summer again. Thank you.
Yes, thank you. Bye-bye.
Thank you. Bye. Okay, so to save some time, so we have our next speaker, Professor Anke Weidenkampf. Professor Weidenkampf is also from Technical University of Darmstadt. Professor Weidenkampf is a fellow of the German Academy of Engineering and German Academy of Science, director for Fraunhofer Institute for Materials Recycling and Resource Strategies, chair of Academic Committee of GCCCD, distinguished professor at TU Darmstadt. So I want to give the floor to Professor Weidenkampf for your talk. Let's welcome. Thank you.
Yes, thank you very much for the introduction. And so I hope that I get my slides, then I can be fast. So, the reason why we are sitting so comfortably here is that we have access to many resources and to a huge infrastructure which takes away all the waste we are producing from under our noses and out of our sight. And we saw this morning also in this production of semiconductors, how difficult this is to remove waste and have a clean environment. But we are not removing it completely. We are just bringing it somewhere else. You all know, and we discussed this morning already, that we are producing waste when we are burning fuels, and this waste, this CO2 as a waste, is giving us all the problems. And also our electronic waste is removed very professionally all the time, and we see this here in China. Everything is very clean, but it is landing up on these waste dump sites, for example in Ghana, where people are living on top of our waste. And that's the reason why we set a lot of resolutions in place, for example, the Sustainable Development Goals, and also, at least in Europe, we have the European Green Deal and the CO pollution ambitions, and we already discussed this, that our friends are now in the COP discussing also other measures of Sustainable Development Goals. So the reason why we are in such a situation in the moment is that we are programmed very linearly, and we have to change this way of living. We have to become much more circular. We have to establish a circular economy. And this was the reason that 5 years ago I started to build up this Fraunhofer Institute for waste recycling and resource strategies. And when I started there, I found out that the recyclers itself, they are also programmed very linearly. And what they call recycling in the moment in Germany is just a removement of waste. And you know that the recycling rates also here in China and everywhere in the world are below 17%. So we have to find ways to change that. And the first step to change it is to have a thorough look on our linearity. And the recycling technologies are also using this kind of very linear schemes. So what we are doing in the moment when we are so-called recycling or doing urban mining is that we are having our waste here in this example, for example, an old mobile phone, and this old mobile phone will then be brought on a sorting machine. This is a large conveyor belt where we are, with a lot of sensors and separating technologies, separating the waste. We are using also a lot of digitalization, so-called machine learning and artificial intelligence to sort this waste. These are huge amounts, also in Germany, several tons per capita. And then we have the robots doing a decision, or the machine is doing a decision of what is economically still valuable or which has to be removed because it's toxic. And then we are separating this so-called recyclate. This is a small part of the waste which we can then use to produce new electronics. And this is only the gold or graphite which we are separating. The rest forms a slag which is very toxic. So in the former times we could use the slag to build roads and downcycle, but nowadays it is not possible anymore because of restrictions. So when we are throwing our electronic waste or part of this electronic waste into the furnace, then we produce only a few part of the is a recyclate. The rest is the slag which has to be deposited. So these recycling technologies we put into place, and we define all these R's, you know them, reuse, recycling, rethinking, and so on, lead to the fact that we are still exploiting nature every day. We are digging deeper and deeper holes into earth, mainly here in China, because you have a lot of resources. And then at the same time, we are dissipating our resources when we are distributing the waste all over the world, and we have these very strategic resources, these metals which we really need for our future technologies, which we discussed today. And so, to my opinion, we have to reverse this cycle. We have to learn to produce out of the waste bin, to use the waste to produce material. So where do we stand today? Also here in China, we are very much depending on fossil fuels, we heard it, and so this means that while we are building up a new infrastructure for renewable energy technologies, we have to rely on the old infrastructure, so we cannot just discard it, we cannot recycle it because we still need it, so we have in parallel to build up a new infrastructure, and here a lot of resources are missing. But the good news is, as we heard also from the previous speaker in his last slide, mankind always finds solution. There are always disruptions, disruptive technologies which are set into place, and mostly, or like in nearly 100% of times, this follows the discovery of a new material. So mankind started, and we saw this also on another slide today, started to find ways to extract materials, metals to produce steam engine first, and then other combustion engines, and we are still relying on these combustion technologies, and but the discovery of new materials and new elements was leading huge disruptions. So that's why we call in history also the times which were following this disruptive findings of new materials according to the materials. So we are talking about the Stone Age, the Bronze Age, Iron Age, the Silicon Age, because we disrupted the whole life with these discoveries. For example, silicon was first discovered and then the computer technology evolved. It was not that someone wanted to invent a computer and found the silicon. It was always the other way around. And that's also, I think, what will bring us into the future. So now we decided for defossilization, but we do not know yet what kind of technology will bring us this new disruption for saving our climate. And but there is a lot of technology around, and we are now already using most of the periodic table for our renewable energy converters. And we have also new materials which we are discovering, for example, these topological materials, like also other quantum materials, which might bring completely new functions into this world, which we do not know yet, but we know that, for example, correlated electrons in solids are very interesting for superconductive electronic transport, and other technologies highly needed. So please visit this website of a friend of mine, Claudia, who's also frequently here in China, where you can play a little bit around with these quantum topological systems. And what I would like to tell you here today is that besides looking on better efficient material and in new materials for new technologies, we have to also consider sustainability into account from this first second that we are developing new materials and new technologies. Because if we are not doing this, we might replace a system of today by something which is even worse for the environment and less sustainable. So if we are not learning to consider sustainability when we are developing new materials and new technologies, we might make everything worse than it is today, and actually we do not have time to make the wrong decisions. So if we are deciding now that green hydrogen is the new fuel of the future and this is wrong, we might not make a corrections in the end. So to my opinion, we have to have the sustainability as a function of the new materials and new technologies taking into place. So if we are making the sustainability evaluation, and this is very difficult because we have in the moment not a metric for sustainability, then we have to have to take the criteria for substitution materials in such a way that we are not only aiming for better performance, higher, faster, and so on, but we also have to take into the ecological footprint into account from the first moment on. So we have to calculate this, and also, of course, economic factors. If this is not payable, the new technology, it will never be taken into place, and also criticality measures have to be taken into account. So the materials of the future have to be more sustainable, they have to be recyclable and regenerative. And how do we do this? How do we get a metric for sustainability? This is by, for example, running a life cycle assessment or life cycle modeling at the same time. And until now, this life cycle assessment modeling was always retrospective. We have to make this prospective, so we have to know beforehand what kind of environmental footprint we are bringing into the world. So, and you know all how to run a life cycle assessment. You have these measures, these impact indicators, which I have shown you in the previous slide. You're running these synthesis or production processes in the computer, and if you have all the data, then you can try alternative processes. And you make an assessment then of these results and bring the results into the system boundary again, and you can improve your material synthesis and production. And you know, as material scientists and chemists, we are so used to just take something, some starting compounds, we make a product, and then we characterize, publish, and forget about it. We really have to take into account now what we are using as starting compounds. And you can also use starting compounds from out of your waste bin to save us a lot of energy and a lot of logistics and so on. So what you can do if you're, for example, producing new and developing new electrode materials for water splitting apparatus, so for the oxygen evolution reaction, for example, then you need high surface area material, here transition metal oxides, for example, and instead of using the classical template, a silicate, you can also use old coffee or old tea as template, and then you can, if you bring the people in the lab to use a digital lab journal, then you can assess the data for every step of the material synthesis, and you can get, for example, these signatures for the global warming for every step of the materials design or geopolitical risk and so on. And you can then identify hotspots which can be replaced by an alternative process. And you see already here that everything can change every day. For example, if there's a war between Russia and Ukraine, then the geopolitical risk for getting nickel, at least in Germany, changes completely. So now it is much more difficult to get nickel than cobalt because of this war. And this has to be taken into account as well. So we were talking about biological manufacturing already today, and nature is doing something else. It is not aiming at more performance, faster and higher, and so on, like we are doing with our electrochemical systems. Nature is more sustainable. It never runs on the maximum efficiency. So photosynthesis runs at very low efficiency, much less than a tree or so could do. And why is nature doing this? Because it is sustainable. It tries to grow better roots and live longer, and so it is never exhausting himself. So such a tree can be at daytime a photovoltaic power plant, and at nighttime a battery, so the photosynthesis runs 24 hours and never at highest efficiency. And maybe we have to copy nature and become more sustainable in this way. So one possibility is to grow batteries on trees, let's say it like this, using bio materials more for our everyday life, but also in our inorganic world we see living matter. So, for example, there are crystal structures like the perovskite crystal structure, which is able to accommodate, for example, more oxygen, and is also able to not being destroyed if you are releasing oxygen. So this type of crystal structure can breathe in and breathe out without being destroyed. And this is then also possible at very high temperatures. When you're using concentrated solar radiation, you can also use these kind of crystal structures to breathe in and breathe out, and it is a new way of converting, for example, the power of concentrated solar radiation. So, you know, the reason why I'm talking about materials for renewable energy converters is also that sunlight and wind is very diluted. So in the end, for the new infrastructure, we need more than 10 times more materials. So we have to find a way first to concentrate. And one way to concentrate is to concentrate solar and then make a converter system in these reactors in the middle instead of just running ranking cycle. And we will hear most probably from Renjin, from our chairman of this conference, about these possibilities. And then I have another point which we didn't tackle here on this conference, and this is that only 0.1% of the temperature on Earth is below 100 degrees C. So we have a lot of geothermal energy where we also might find future energy converter systems which are more renewable and more sustainable than the converter systems we are using nowadays. So, and if we find a heat to electricity converter system which is better than the mechanical one now, then this would be a huge solution. And there is such a device, and this is a direct thermoelectric converter system. So now, in the moment we make thermoelectric conversion by just first having a system which produces mechanical energy, and then in the next step we produce the electricity with a generator. But with a thermoelectric generator made of thermoelectric materials, we could do this in one step, and this would be more efficient and more sustainable. And how do you do this? You connect P and N-type semiconductor systems in a clever way so that you can then make this energy conversion process with by adding the entropy on the charge carriers which are moving. And you don't need a liquid, you just use the charge carriers, and you can provide a huge temperature gradient on such a system. And of course, we cannot beat thermodynamics. We also have the Carnot efficiency as the upper limit, but if we provide materials which are better than the materials we have today, we might end up with a very good high temperature converter system. And we tried, for example, to use this for concentrated solar radiation when we are making endothermal processes in such a solar converter system where we are shining concentrated solar light, or in this case in the lab, of course, just the lamp, into a cavity reactor where we have then conversion of hydrocarbons, for example, and then we cover the surface of this reactor with thermoelectric generators, and we can co-generate some electricity here in this high energy density converter system. So I will not talk so much about thermoelectricity. You will hear a talk of my colleague Wenji Shi tomorrow, so I will skip this a little bit, but I will tell you that we have found some perovskite-type thermoelectric converter systems where we can breathe in and breathe out during the heating and cooling of this solar reactor. And we can also use this as for cogeneration in solid oxide fuel cells. Like here, we could add this converter directly in an open flame, and you see it can sustain these large temperature gradients and these severe conditions in a flame. So these perovskite type materials, as I said, they are regenerative, so you can switch, so it's not running. You can switch places and you have a very correlated system and use them as mixed ionic electronic converter system, and this is the key for solid oxide fuel cells or solid oxide electrolyzer systems. It's also the key for other CO2 reduction processes or solar-driven processes, and we have to design this material in a certain way, and we are trying this since many years. You know, the semiconductor design of these perovskite type materials depends very much on the electronic structure and how to control the electronic structure of new compounds. And here we define this collaborative research center, or in German SFB, on Fermi level engineering, where we are trying to understand and apply a new direction of developing these mixed ionic electronic conductors by using this common energy scale, the Fermi level. And I cannot go into detail, but as I said, when you will do this tomorrow, we can design like this also new thermoelectric materials. So here, for example, on basis on this very sustainable calcium titanate crystal structure, so we are adding a little bit europium to have this steep rise of at the density of states, so meaning putting a lot of entropy on the charge carrier in this case, and we design new materials like that. And as I said, we want to take the sustainability into account, so we are developing material which are made out of the waste bin, so we cycle these materials, these electrocatalyst, electroceramics. We build the thermoelectric generators, and then they can be recycled to a powder which can then be used for a new thermoelectric generator. And you see here, the more we place, the more dirty this compound is, the more ions we place on one position, the better the figure of merit is, so the performance of the material. But I told you in the beginning, we don't aim only at high performance, also on high sustainability, but this very dirty material is also easier to recycle. So we could achieve both better performance and better recyclability. And I could give you a little more examples for that, also for this test case, a new membrane material for different applications, where we are designing the new material by applying this Fermi level engineering approach. And you can see we can increase the flow of oxygen in such membrane materials. Why do we need membrane materials? Because another key of the energy conversion process is that you can separate the gases which you're producing in such a splitting moment. If you're splitting water, or in this case CO2 from air, to produce new starting materials, it is the same. So here we are igniting CO2 plasma, and in the CO2 plasma we convert carbon dioxide to carbon monoxide and oxygen, and so we have to prevent the recombination of these two gases, and we need a very good performing oxygen conductive membrane material, and this will be presented by my co-worker Guoqing Cheng tomorrow. He is producing these membrane materials in a way that we can also use as starting materials, not chemicals purchased, but using the materials from the waste bin. So here we can use old ceramic membranes and we dissolve them. We can use this aerosol reactor to produce new perovskite type powders, so we could show that it is in principle feasible to recycle this material. But the bad news is that it costs, of course, a lot of energy to recycle, so you have to put in new chemicals and new energy to recycle, and in the end, the production of recycled materials costs you more if you're running the life cycle assessment than if you're using primary resources. But clearly, it is also a very new approach to do that, and to tell the students, don't take primary chemicals, use the waste bin. This is also clearly something which goes against the second law of thermodynamics, because we always have to produce entropy, and it costs us a lot of energy to purify again. So that's also the reason why waste is such a problem and will stay a problem. We cannot close cycles, because in the end we have to produce the entropy. So, but we can do better than we do today, and we learned this also today here. So there's also one way to recycle plastic waste or bio waste. We heard one idea that we are decomposing it into gases, but our approach here is to remove the gas, the hydrogen, and get the carbon as a solid instead of having CO2 again. So the solid carbon can then be used, for example, to produce new batteries, or we can just put it back to the ground, and the hydrogen is used as a fuel. So here Goching is using another plasma flame. So here he is igniting a plasma, and he can throw in a lot of plastic waste from textiles to old medical waste, and when he's using the right catalyst, he can produce a carbon nanotube composite material and hydrogen, which is then used in other applications, like, for example, metallurgical applications directly. And so we are trying to combine these carbon cycles with the hydrogen cycles to a more sustainable application of renewable energy. Thank you very much.
Thanks so much, Professor Weidenbach, so for saving some time for us. So because the time is run a little bit behind the schedule, it's my fault. Actually, I do not control the time, because I just want to give a speaker more time to share their knowledge here. But with that, so we cancel the coffee break time, but the coffee break is served outside. So if you want to have a coffee or get some snack, feel free to go outside to pick some. And we will continue our next session. So next session will be chaired by our colleague here, Professor Cheng. So I want to give him an introduction here. Professor Cheng is a professor at Xi'an Jiaotong University, Deputy Director of State Key Laboratory of Multi-Phase Flow in Power Engineering. And 陈斌老师是西安交通大学教授、博士生导师，那个动力工程多项流重点实验室副主任。现在我们有请陈斌老师给我们主持下个阶段的这个报告。Welcome.
Thank you very much for Chairman Professor Xu's kind introduction. And I will chair the second plenary session, and we have 5 plenary talks in this session. And the first plenary speaker is Professor Chunbao Xu. Professor Xu is currently chair professor of advanced biorefinery at the City University of Hong Kong, fellow of Canadian Academy of Engineering. He has over 20 years of research experience in conversion of biomass and organic solid waste into biofuels, green chemicals, and biopolymer materials. He was the NSERC FP Innovations Industrial Research Chair in Forest Biorefinery at Western University. And he is the recipient of the 2011 Syncrude Canada Innovation Award and the 2019 Award in Design and Industrial Practice from Canadian Society of Chemical Engineering, and the 2023 Humboldt Research Award。徐春宝院士呢是加拿大工程院院士，香港城市大学讲席教授，他主要从事生物质转化技术、生物质能源、生物质及化学品材料开发利用研究。徐院士曾任加拿大西安大略大学化工系终身教授、加拿大国家级工业讲座教授和林业生物炼制首席科学家，先后获得日本能源学会优秀青年科学家奖、加拿大化学工程协会加拿大创新奖及工业设计和实践奖、加拿大新风采创业奖、德国红宝奖等荣誉。And the title of his presentation is the role of biomass and organic solid waste energy utilization in achieving China's Dow carbon target. Please.
Okay, thank you, Professor Chen, for a nice introduction. As I said, so we're running behind the schedule, so I will do my best to reduce the time. Okay. Okay. So first of all, as the chair introduced, so I am honored to receive the prestigious award from Humboldt Foundation, so the Humboldt Research Award. So that's why. So I visited Technical University of Darmstadt in the past summer. A little more background about why biomass or what biomass can do. So I want to advocate how important the biomass can contribute to the sustainability and the carbon neutrality. So this is the mapping. So show that roadmap. Show that the carbon neutrality in China and also in the world. We know that China has a target, 2060 target for carbon neutrality, and Germany has the target 2045. It's more ambitious, although the countries did not pledge for this, but they aim for that to achieve the carbon neutrality 2040. And in terms of biomass, so the role of biomass, first look at the biomass resources. Biomass has a huge resources. Every year produce more than 220 billion tons of biomass naturally. So this biomass, it can meet the 10 to 15 times world energy demand. How can contribute the carbon neutrality of biomass, so we can actually summarize here. So it can directly burn to generate heat, thermal energy. And more important, biomass can be a feedstock to supply to a biorefinery. This biorefinery can produce bio-based fuel, chemical materials, and can substitute for fossil fuel to reduce the CO2 emission. So this is how biomass can contribute. In terms of biomass resources in China, so this slide shows actually, this slide already given, some information given by Professor Guo in Professor Guo's talk. So China has more than 3.5 billion tons of solid biomass and organic solid waste. It's equivalent to 460 million tons of coal, standard coal. So this can actually, if you utilize those energy, can reduce the CO2 emission by 0.9 billion tons, or now, or in the future, it grows. In the future, 2060, can have potential to reduce more 2 billion tons of CO2. So it can be contributed huge for this in China only. And this slide gives the diagram, actually a summarized diagram for a journal, engineering. So it's a journal of Academy of Engineering in China. So we have a perspective to give them how biomass can contribute to larger scale energy storage. So biomass actually can provide the carbon, the renewable carbon, and then can actually integrate it with the green hydrogen to convert the green hydrogen to liquid fuel or to methane through methanation. And then those methane all those methanol or green fuel can be transported easily from the west part of country to the southeast part of country. So this solves the transportation issue or the energy storage issue. And some of the summaries about my own research. We have done research for more than 20 years on biomass conversion, and then what type of work we have done in terms of biomass conversion to energy, to bioenergy. So I just give a few examples, showcase our research. So first is conversion of biomass and bio-waste to bio-crude oil through hydrothermal technologies. So this is the diagram show the different conversion routes and different technology applied by developed by our research or industry society. So in terms of conversion, we have one type of conversion called the thermochemical, and among that is hydrothermal technology is the technology we have been focused in the past more than 10 years. So including hydrothermal liquefaction produced by crude oil, hydrothermal carbonization to produce hydrochar, and hydrothermal gasification to produce hydrogen. And in terms of temperature, so this technology involving hydro means water. So water is reaction medium, and then in terms of temperature and pressure, so if you do the reaction at above the critical point, just like Professor Gore discussed in the morning, in early presentation, so supercritical water gasification can gasify the biomass to produce green hydrogen. But if you reduce the temperature or pressure to below the critical point, and we can utilize the subcritical water to liquefy the biomass to produce bio-crude oil. And then if we further reduce the temperature and pressure, we can do the carbonization to produce the hydrochar. So this is the technology about the hydrothermal. And in the past, we have done many research about using different feedstock, different waste to liquefy the biomass. So this is shown here. So there's agricultural biomass and woody biomass. And we also worked with the food waste, liquefaction, wastewater sludge, and microalgae. So those conversion to bio-crude oil has been published in this paper. And in terms of the reactor, we developed a continuous flow reactor as shown in this picture. So we developed a 6 kilogram of per hour liquid feeds of the feeding reactor, continuous operation. So this reactor has been scaled up in the past 3 years. We have been working with the Jiangxi Academy of Science here in Nanchang. So we developed the technology and then to 100 kilogram per hour, the scale. And now this facility is operating in here, so in Jiangxi Academy of Science. If you are interested in this, so we're welcome to visit this lab. So we have a facility here running on hydrothermal liquefaction. And more recently, we established a company. So advanced biorefinery technology to further commercialize this technology, the hydrothermal liquefaction technology. So we are now in the stage of designing and commissioning the 10 to 100 ton per day hydrothermal liquefaction plants. Our goal is to produce bio-crude oil and also upgrade the bio-crude oil to some jet fuel or some marine biofuel to meet the requirement for the sustainable aviation fuel and the green marine fuel industry. And this is the diagram show the design. So we want to design we want to manufacture the 10 ton per day hydrothermal technology to convert the manure, the pig manure or the cow manure to liquid product, which is a bio-crude oil here. Another technology we have done is the hydrodeoxygenation for upgrading. So those oil has the problem, this bio oil has a problem. Doesn't matter the bio is from pyrolysis or hydrothermal liquefaction. The oxygen content is much higher, it's way higher than the petroleum heavy oil. So this makes a heating value much lower than the petroleum. So we need to upgrade this oil to high quality oil. With that, so we can do different technology, but we focus on catalytic hydrotreatment to remove the oxygen to enhance the heating value and to reduce the viscosity and improve stability of this oil. The facility we develop in our lab is the deoxygenation reactor. So we can feed the reactor with hydrogen, high pressure hydrogen, or we can feed the reactor with some in situ hydrogen to upgrade the oil. The one research we have done is we investigate the effect of different hydrogen sources. So we compare the hydrogen gas, ex situ hydrogen, and in situ hydrogen, which is formic acid in this case, compare their performance in upgrading the bio-crude oil to high quality oil. The research actually performed in the lab. So we have done that. We have done an experiment at different temperature, and we found that this oil can upgrade. So the O by C value can be reduces significantly to 0.1 from 0.8. And then H by C value almost maintained the same high value here. So which means this oil can be upgraded. And we also find that the in situ hydrogen source is performed better at a lower temperature than the high pressure hydrogen in terms of upgrading. We developed some new catalysts for this purpose. So we use a multi-wall nanotube supported nickel, molybdenum, tungsten, the catalyst. And we found this catalyst perform better than the other type of catalyst. So this has some of the opportunities for future applications. So this catalyst is much better, even equally good as the ruthenium carbon, the commercial catalyst. And this slide shows those multi-wall nanotube support the catalyst can actually achieve very low O by C value. So the quality of O has been significantly improved. And in terms of hydrogen production, so we have done some work on the producing hydrogen, green hydrogen from biomass. So hydrogen has color, we know that, but hydrogen, we call it green hydrogen, normally actually classified by the scientific the community by the hydrogen from the renewable electricity, for example, the wind power or solar power. But actually, we want to actually advocate that the hydrogen from biomass is also green. It's also from solar power, because biomass is from solar. And this is a roadmap show the hydrogen production technology suggested by US DOE. Based on US DOE, in the near or midterm, biomass gasification to produce the hydrogen is still dominating source for hydrogen. So this is very important in terms of US DOE's roadmap. For biomass gasification, we have done a research on the catalytic gasification of biomass using the fluidized battery reactor to the scale of 10 to 20 kilogram per hour. So we produced a little bit larger scale hydrogen using the fluidized battery reactor. And we tested different catalysts as better materials. The olivine limestone has been picked up as the best catalyst for this gasification. And in terms of supercritical water gasification, I think the early presentation by Professor Guo already talked about this. So we can gasify the biomass in terms of here, we use the glucose as a model compound. So 1 kilogram of glucose can produce 1.5 cubic meter of hydrogen. And we develop a facility, the continuous flow supercritical water gasifier, to achieve this highly efficient the gasification of biomass using supercritical water. And some of catalysts, heterogeneous catalysts, for example, nickel, ruthenium-based catalysts, we can achieve very high efficiency. For example, almost 100% efficiency, carbon gasification efficiency, at 600 or even below. And the hydrogen content is very high, close to 60%. This shows the catalyst stability. So we test the catalyst, some catalysts, in this case, ruthenium modified nickel catalyst can achieve 4 days continuous operation without sacrificing the activities. Application of biomass for iron and steel making industry is another project we have been working in the past. So the iron and steel industry actually is one of the most major contributor to the CO2, if you look at this. So energy sector contributed 73% of CO2 emission among all the industry of the human activities. But the iron and steel industry contribute 30% out of the total industry contribution. So which means the iron and steel industry is a major, is the most important, the CO2 emitter. With that, so we propose, actually we have done some research to use the biomass, but through those different approaches. So we can do the fractionation to get the lignin cells and we can convert lignin as a biomass iron pellets. And also we can use the cells to produce adhesive, to produce a CMC pellet adhesive for the iron and steel industry, as well using the hydrothermal carbonization to produce biochar as a blast furnace injection fuel. And we can also activate the biomass to get the activated biochar and then to use as a metallurgical flue gas treatment. So this is how we utilize biomass to control to reduce the CO2 emission. With that, I want to conclude my talk with this slide about my team. So we have many students contribute to our research in terms of biomass utilization. And thank you. I hope I saved some time for you. Thank you.
Thanks, Professor Xu, for his very good time control. We have 6 minutes saved. So the next plenary speech will be presented by Professor Ivan Fleet Zechurch. His activities include high resolution X-ray imaging and the development of customer solution for a broad range of applications, including package failure analysis, metrology, and inspection in microelectronics. He is a consultant with hands-on experience in the fields of advanced materials, nanotechnology, and microelectronics, as well as process control and quality assessment. He holds honorary professorships for nanomaterials at the Brandenburg University of Technology and for nanoanalysis at the Dresden University of Technology. He had several management positions at Airbus, at Advanced Micro Devices, at Frankfurt, and as a startup DeepXScan. He is a member of the European Academy of Science and member of the German National Academy of Science and Engineering. In 2019, he was awarded with the FEMS European Materials Golden Medal. In 2023, with the DGM Pioneer Award and with the Roland Mitchell Prize. This Czech 教授呢是德国工程院院士，德国勃兰登堡工业大学教授，德国弗劳恩霍夫陶瓷技术与系统研究所微电子材料研究所的所长。他的研究领域呢包括高分辨率 X 射线成像，以及广泛应用的开发定制解决方案等等，也获得了多项的荣誉和奖励。OK, please.
Thank you very much, Mr. Chairman, for these kind words. Yes. And it's a great pleasure for me to be here in Nanchang, and thank you to the organizers for inviting me. In all the talks about energy technologies, we got the message that's all about materials, and my talk today will be about materials and the understanding of materials based on microscopy and a particular technique that's X-ray microscopy. Let's start with X-ray microscopy and nanocomputed X-ray tomography, and this will follow with some examples, electrocatalysis and batteries. In this century, there are 4 technical megatrends. It's energy and mobility, resources and raw materials, information and communication, and biotech medicine. And for this, we need key technologies: informatics, biotech, and materials. And materials is one of the key technologies, and materials and process characterization are necessary for all these megatrends, and particularly for energy technologies. I wanted to show now that particularly microscopy is a field which enabled new technologies and new innovations. I think all of you know light microscopy with a resolution of about 200 nanometers, and we know it since the middle of the 17th century. It was the basis to image bacteria, and for instance for Robert Koch to fight against diseases like tuberculosis. In electron microscopy, we can get down to atomic resolution. First electron microscope was built by Ernst Ruska, 1931, and this brought really breakthroughs in solid-state physics, material science, cell biology, and in 2D microelectronics. And there's a missing gap, and this missing gap can be filled with X-ray microscopy in the laboratory today with a resolution of 50 nanometers, but with the possibility of going down to 10 nanometers and below. The first synchrotron radiation experiment was performed by Günther Schmal from Göttingen, and this technique allows to image buried structures of opaque materials. We can look really inside the objects with high resolution, and therefore it is a way to get information about material science, energy technologies, 3D microelectronics, and system biology. So what you should have in mind if you hear X-ray microscopy, that is a combination of resolution and object penetration. It's high resolution, it's non-destructive, and it's three-dimensional. I want to show 3 examples what you can do with this technique. The first one is from microelectronics. What you can see here is the design, the interconnects on the chip from an Intel microprocessor. So we can really look inside the chip without destroying the chip, and then you see the real microstructure of the design. The second example in the middle is a battery material. The green part is a cathode of a battery, and you see the individual particles of the cathode and the open volume in between. The third example is from biology. This is a diatom frustal, as you can find in small rivers and in lakes. And here you can learn how nature builds these inner structures, and you can learn for structure mechanics, so without destroying the object. After these 3 examples, I would like to remind you about X-ray computed tomography. I think you all know it from medicine. It's a non-destructive technique to look into our body, and with this technique, which is used in medicine, this is based on the same geometry as Konrad Röntgen used more than 100 years ago. It means you have a small X-ray source, you have an object, and you have a screen. It's pure projection geometry. With this pure projection geometry, you can get down to a resolution of about 1 micrometer. If you want to get a resolution of 100 nanometer and less, left-hand side, really nano resolution, then you need a microscope. And the microscope has optical elements. You need X-ray optics to focus the X-rays. That's the way to go, and this is what I'm talking about today. And these X-ray optics particularly have one important part. It's the X-ray lens. And X-rays you cannot focus like visible light with a glass lens. This is because the refractive index is one for all materials in the X-ray range. You have to use other physical principle. And one physical principle that you can use is diffraction, not refraction like visible light, it's diffraction. And that's then so-called Fresnel plate. As you can see, this is a system of hundreds of concentric rings, and at each ring you have a diffraction process. X-ray microscopy is based on two discoveries. The first one is from Ernst Abbe, the second one from Konrad Röntgen. Abbe's theory of image generation means that the resolution of an optical lens depends on the wavelengths and the numerical aberration. Numerical aberration you cannot change so much, so wavelengths is the way to go. That means if you want to go to better resolution, lower values of D, then you have to reduce the wavelengths or increase the energy. That means go from the visible light of electromagnetic radiation to the X-ray range. The second discovery is the discovery of X-ray absorption. Actually, this was beginning of November 1895 when Röntgen discovered the X-rays, and 6 weeks later he had the first image of the hand of his wife. You see the metal ring that absorbs all X-rays, the bones that absorb reasonable part of the X-rays, and the soft tissue nearly nothing. This I think you all know. This is the same you can use in technical applications. Steel, because iron has a higher atomic number than aluminium, is absorbing more, and the thicker the object is, the more absorption you have. By the way, since we are talking about innovation here also, this is from my point of view the fastest technology transfer ever, from the original discovery of X-rays until the application 6 weeks. Very often people ask me why it took so long until X-ray microscopy became an imaging technique. There are two reasons for this. The first one, there were always arguments against X-ray microscopy, and even Ernst Ruska, Nobel Prize winner, he said there are no materials for the construction of X-ray lenses with sufficient refractive power because the refractive index is close to 1. The second part of the sentence is correct, because if you see the complex refractive index, delta and beta are very small, so for all materials is practically 1. However, and then he directed many researchers in the wrong direction, because they said, okay, it's not possible to use X-rays for imaging. But it is possible because you can focus also with reflection or with diffraction. Today, mainly diffraction is used, and as I said, with such lenses, and these lenses have very fine structures. If you want to get a resolution of 50 nanometers, then the outermost ring of this Fresnel blade of this lens has to be in the range of 40 to 50 nanometers. And to manufacture this, it was necessary to have the manufacturing technologies from microelectronics, lithography and etching. And this was for a long period of time not available. Therefore, X-ray microscopy is such a young technique. Now, some words about the evolution of materials and material science. It started with homogeneous materials. Homogeneous materials, for instance, is bronze and steel. Then we had a period of composite materials, but more and more we study hierarchically structured materials. We design new materials, and for these materials we need a complex characterization. The morphology or the microstructure with microscopy, the composition, chemical bonding with spectroscopy, and the atomic structure with diffraction. And here I'm talking about morphology, and this can be studied with X-rays, with tomography. Tomography means you have a principle where you have a superposition-free cross-section. Yeah? It's not that you have only one projection and then a superposition of many elements and you don't know what is where. You take a lot of images, a large number, and then with a numerical procedure, with 3D reconstruction, you can gain virtual cross-sections and characterize the individual element in the interior of an object. Tomography works very well if the ratio between sample thickness and resolution is in the range of at least 100, better 1000. So here you see the sample thickness in the x-axis, you see diagonal, the typical lateral resolution, and then this ratio. For light microscopy, the ratio is 1. Therefore, with a light microscope, you see the surface, nothing more, so it's two-dimensional. If you have an electron microscope, a TEM, then you can also tilt the sample and do some tomography. There you have a ratio of about 100. It's fine for tomography. However, you have always to prepare a very thin sample of about 100 nanometer thickness, so it's not really non-destructive. In the X-ray range, you have usually a ratio of 1000, and the thickness of the sample, how large the object is, depends on the energy of the X-rays. And since we have 3 orders of magnitude of the energy range, so it's an ellipse and not a sphere there. So the message is X-ray computed tomography is multi-scale, it's 3-dimensional and non-destructive. And I'm focusing here on the left part, this nano X-ray computed tomography based on a microscope with an X-ray lens. After the first part of the technique, I show now 2 examples. The first example about electrocatalysis. We all know that materials innovations are needed to maximize the energy conversion efficiency of processes. These processes work, but they are not efficient enough. So, for instance, for water splitting, we have to use, in the best case, renewable electricity and convert this renewable electricity in storable chemical energy, and this, for instance, with a water dissociation process with water splitting. And one very new material is a platinum-free electrocatalyst that was used by Xinjiang Fang's group in a technical university in Dresden. And there you have a hierarchical structure. You have a nickel foam. Then on this nickel foam, there are oxide columns. There are oxide columns grown. And then on the surface of these oxide columns, here in this case molybdenum oxide, you have molybdenum nickel nanoparticles, and these are the electrocatalytic active elements. And the process how to manufacture it is that you have a mixed oxide, a nickel molybdenum oxide, then a thermal process, and then at the surface you have an out diffusion of the nickel so that the column is only molybdenum oxide, and then at the surface you have the molybdenum nickel nanoparticles. What are the requirements for such a system? It's on the one hand side performance, that means electrocatalytic activity, and on the other side reliability and lifetime, that's electrochemical stability. It means if you see these directions of development, on the right-hand side, you want to have an increasing intrinsic activity, means low hydrogen evolution reaction, fast Vollmer step, and Tafel step. For this, you have to understand the surface physics and surface chemistry. This is determined by mainly by the crystalline structure. On the left-hand side, you want to have an increasing number of active sites. For this, porous structures are beneficial because you can get a large surface area and a high mass transport. For this, not electron microscopy is the right technique, but X-ray microscopy. And I want to show 3 examples of this multi-scale X-ray tomography. Here you see the foam structure and micro-XCT in the lab. Then you see these columns that are grown in nano-XCT in the lab. And with the very best resolution at the synchrotron, you see the catalytic particles. So that means with such a study, you get morphological information about this electrocatalytic system, 3D information, possible quantitative data, and this quantitative data is the active surface area, it's a size distribution, as porosity and tortuosity. Second example is a battery material for battery cathodes. There are 3 elements that are of interest that we want to study. The first one is 3D morphology, the 3D morphology of the cathode. In the middle, you see that it's possible to determine quantitative parameters, 3-dimensional parameters. Porosity you can also determine with other techniques, but not tortuosity. Tortuosity describes the interconnectivity of the pores. And if you have porosity and tortuosity, then you can determine the effective diffusion coefficient for the within the lithium, for instance, in the battery, the electrolyte. And on the right-hand side, you see an example for reliability and lifetime. This is damage of these particles in the cathode and cracks. This I will show in a bit more detail. We have brought a cell for electrochemical processes into the X-ray microscope, so that we are able to cycle the battery. That means we have loading, unloading cycles. And in this cell, we have all the elements. We have the cathode, the anode, the separator. So it's a working battery. And what you can do then, you change the cell potential during the cycling, and you can see how, for instance, cracks in these particles are developing. And in a better way than in the scheme, you see it if you use the 3-dimensional information that you get from tomography, and then you can, in each plane that you want to have, do a virtual cross-section, and then you see after several cycles how these cracks are developing, and then with image analysis you get the opening of the crack, the length of the crack, and you can learn. What we found, the commercial battery material, that the probability that such cracks are formed, that reduce the performance and then also the lifetime, that this probability depends very strongly on the size distribution of the particles in the cathode. That means if you find a process to make the size distribution more defined, you are able to increase reliability and lifetime, which is really a contribution to sustainability. Imagine if we can increase the lifetime of our batteries by 10%, it's a huge economic factor. Summarizing the battery part, I want to say that with the battery part, it is possible to quantify 3-dimensional parameters. This is battery performance. And with operando studies of kinetic processes, it is possible to understand degradation mechanism that limit the lifetime of the batteries. And with this, I come to my final summary slide. I wanted to show that materials are the key technology for energy storage and conversion, that nano X-ray computed tomography and X-ray microscopy are able to study morphology, and since this technique is non-destructive, different to all other analytical techniques and microscopy techniques that we know, it is possible to study kinetic electrochemical processes. It is possible to determine quantitative parameters like porosity, permeability, and tortuosity, and we get with this very valuable information as input for modeling for fluid dynamic transport processes, for instance in batteries or fuel cells or in other systems for hydrogen storage. With this, at the end, I would like to thank my X-ray microscopy team in Dresden and my collaboration partners who contributed to these results from Helmholtz Center Bessie in Berlin, from Technical University in Dresden, and from AGH. This is the largest technical university in Poland, in Krakow, and thank you for your attention.
Okay, let's thank Professor Zachurch for his nice talk on the theory and innovation on X-ray imaging, as well as the application in different energy materials. And also he saved 5 more minutes. And the next speech will be given online by Professor Zhengmeng Hou, who is Michelle Zhengmeng Hou is a fellow of the German Academy of Geosciences and Geotechnical Engineering, tenured professor and Karlsruhe University of Technology. He specialized in teaching research and international cooperation in areas such as deep rock mechanics, clean underground energy development, hydraulic fracturing for unconventional oil and gas, and deep geothermal resources, carbon neutrality and energy transition, large-scale underground storage of natural gas, high-pressure air, strategic petroleum, hydrogen energy, and renewable energy. His expertise also includes integrated underground space utilization, CCUS, thermal conduction, multi-phase flow, rock mechanics, geochemistry, and the coupled process in rock masses, as well as numerical simulation. 侯正猛教授呢是德国地球科学与原土工程院院士，克劳斯塔尔工业大学的终身教授，他主要从事深部岩石力学、地下洁净能源开发、非常规油气和深部地热的水力压裂、碳中和与能源转型、天然气、高压风、战略石油、氢能和可再生能源的大规模地下储存、地下空间综合利用等等方面的教學科研和国际合作。Professor Hou are you here?
Yes.
Okay, please. Please.
Okay. Can you see and hear me?
Yes, very nice.
Okay. Thank you, Professor Zhang, for your the introduction. And ladies and gentlemen, thank you all, especially I must thank Professor Charles Xu for your invitation. I'm now in Germany at TU Clausthal. That is my presentation, CCCUS, Carbon Capture, Circular Utilization, Regenerative Biomethanization and Sequestration in depleted oil and gas reservoirs. I see also a few German colleagues and guests, but the most of the audience are Chinese. Therefore, I will switch to the Chinese。我的题目是碳捕获循环利用用于地下再生天然气和地质工程。那么4个部分：引言、常规的CCUS 和我们创新的 CCCUS 以及节能与展望。那么这个我想大家都非常的熟悉，所以就不需要多讲。中国是最大的碳排放国，我们的自然碳汇啊，大概现在只有11到12亿吨，那到这个2060年时最多只能增加到14亿吨。我们但是这个中国这2年的风光装机容量发展速度是非常巨快。那么我们的比如说电气化，在2021年是26%，到2023年就增加了1个点27%。那么全社会的耗电量，2021年是8.5万亿千瓦小时，2023年已经达到了9.2万亿千瓦小时，占了全球总耗电量29.5亿千瓦小时的31.5%，这个占比与中国制造业占全球制造业的占比差不多。那么风光发电量占总发电量的2021年才11.5%，2023年已经提高到15%，估计今年2024年将达到17%。那么今年的去年的风光2个新装机容量已经达到了3亿千瓦，那么今年将会要达到4亿千瓦。这2年来的这个风光装机将会新增发电量，今年7000亿千瓦小时，那么会超过我们的总的这个增加量，所以今年我们的煤炭发电量将会大大的下降，中国可能是今年就会达到碳叫做什么高峰。那么为了实现电气化，中国将为了实现碳中和，中国的电气化程度将由去年的27%提高到70%，社会就是电力保障能力将会从9.2万亿度电提高到30万亿度电以上。那么风光发电量在2060年占比达到了85%，这因此需要储存电力6到7万亿度电。由于风光电的随机性和波动性，所以这个储电的这个相当于要占到20%以上。那如果我们比较德国2045年实现碳中和以及中国2060年实现碳中和的能源生产和能源消费结构，可以看得出来，德国是100%的可再生能源，因此没有碳排放。那中国还有15%的这个化石能源，其中根据我们的研究，煤炭占12%，天然气占3%，石油没有，到2060年石油只是化工原料，而我们相当于要生产50万亿度电或者千瓦小时。在消费端可以看得出来，主要是3种形式。电力，德国是75%，中国是70%，占据了30万亿度电。到时候我们的消费占全球消费量40%，去年是31.5%。那么氢2个国家占比一样，当然总量不一样，都是15%。我们是6.5万亿度电，相当于1.3亿吨。地热直接利用加上热泵运用，中国是15%，德国是4%。那么我们根据双碳技术路线，我们决定的6大优先， 可以看得出来，提高能效和节约能源优先于可再生能源，就地的优先于远程输送的可再生能源，这就是分布式能源。可再生能源当然优先于碳吸收，而中国到了2060年还有24亿吨的二氧化碳排放，这个二氧化碳排放必须通过自然和人为碳吸收来中和，其中自然碳吸收以及碳汇作用大概是14亿吨，人为就是碳吸收就通过所谓的负碳技术需要10亿吨，这个量是非常非常巨大的，因为全世界去年也就1000多万吨。碳排放当然优先于碳吸收，而电气化优先于氢气化，然后再优先于这个地热直接供热。那我们现在看看常规的 CCUS， 当然这是用于大家都很清楚提高采收率，特别是石油的采收率，这个是赚钱的，而其他的部分都是属于目前没有补贴，都是属于亏本的。那他们的封城机理我们大家都非常清楚，一个是结构封城，一个是参与贸易封城，还有用检封城以及矿封城。当然时间上来说，矿物封城是需要的时间是最长的，几百年到上千年。它的来源是也是集中排放、集中扑活和空气中直接扑活，而这个的成本现在是每吨300美元以上，所以非常的巨大。它面临着经济方面、技术方面以及市场与政策方面的挑战，特别是这个技术方面，对二氧化碳的高程度要求以及二氧化碳封城的低效性，目前还没有解决。那么我们创新的全球首创的 CCUS 是什么呢？ Carbon Capture, Circular Utilization and Sequestration。 它主要是用二氧化碳，也就是我们前面第一个报告就做到了二氧化碳的utilization 的问题使用。我们是把这个集中排放源，比如说煤电厂的二氧化碳结合以后不需要提纯，再与含氢工业这个伴生气来与微生物来一起注入到我们的废旧的油气厂里边，然后关紧1年左右深化合成天然气、再生天然气、抽采天然气，然后其中一部分二氧化碳还和其他的这个比天然气和重的就是当做了电气，它会进行这个封尘，部分的封尘，也这是二氧化碳抽采以后相当于是储存，抽采以后它会燃烧以后还会再结合扑活二氧化碳，可以再利用，循环再利用，当然每一次有封尘。那这种 CCUS 它的非常具有创新性，即很多功能，主要的功能包含深化合成天然气，同时实现二氧化碳协同微生物强化油气开采，二氧化碳低封尘，再生天然气大规模地下储存，含氢工业废气的大规模经济利用，大规模经济利用非纯度的氢气，也是属于工业副产气和二氧化碳，把二氧化碳资源化与能源化的循环利用等等多种功能。这些文章已经在用中文和英文的发布了，特别是在这个英文期刊上，中文只有一篇文章。那么它的主要功能，其中的第一个就是枯竭油气厂中二氧化碳深化合成再生天然气。这个公式是大家非常熟悉，也就二氧化碳跟4个氢气合成了1个甲烷和2个水，其中它是高放热。这个地方我们主要的采用的 这个催化剂，就是氢酝酿型产甲烷古生物菌。这种古生物菌，它实际上也就是本身油气形成的过程。当然，油气形成是需要2亿年，而我们这个是只需要1年。那在这个油气开采，也就是说协同微生物强化油气开采，它主要是在油厂里边，是为微生物降解原油，把由于油这个石油啊，它是粘度太大，回收率很低，一般呢也就是30%几。那么我们可以降解成天然气，也就是甲烷，这样子啊就可以开采，就非常的容易。那么同时这个关键以后啊，二氧化碳它本身是偏重的，它比我们的这个天然气重，那所以啊，二氧化碳会下沉，天然气生成的天然气会上升。那么二氧化碳地质封存，这就是我刚刚说的，特别是作为电气，二氧化碳作为电气以后再来地质封存，那么这是最主要的，溶解矿化封存是次要的。然后它的第4大功能就是大规模地下储能，因为我们需要大量的天然气地下储集库，这是长时储存，这个是在世界上是早就有范例，已经65年了。那么不仅是在德国、欧洲、美国、日本，也在中国有大量的成功范例。那我们这个相当于顺便就建造了地下天然气储集库，当然是再生的天然气。那中国有没有大量的含氢工业副产气呢？有，根据我们的通过爬虫软件这个找到的2021年中国的所有的这个不是所有的哈，绝大部分因为我们不可能找到所有的数据，那么它的工业副产气里面含氢量是2000亿立方米，这个是非常巨大的，这是一个宝库，到现在为止并没有采用。那这种这个方案是不是计算可行呢？确实是可行的，因为是属于一种无意之中的，就是无心插柳柳成荫。这在90年代在捷克的一个含水层里边建造这个城市燃气的储集库。城市燃气它实际就相当于中国的煤气，它里边主要含的是氢气54%，那么二氧化碳是11.7%，甲烷是21.9%，它储存在这个含水层里边，地下含水层里边，它是没有天然气的，只有盐、水和古生物菌。气轨以后抽采出来，因为它是储集库，抽采出来以后，然后再测的这个气体的成分，发现氢气大量下降，二氧化碳也一样，而这个甲烷是差不多翻倍。那么怎么来解释这个事情呢？通过室内现场同位素监测表明，产甲烷的古生物菌主导了就是再生天然气含量的升高。我们可以从这个上面看得到，如果我们只用地层水，就是在这个250小时，它大概就能够达到50%的甲烷化率。如果是我们使用蒸馏水加10%的盐粉，它就可以达到54%。而如果我们用地层水加10%的盐粉，它可以达到70%的产甲烷率，这是非常了不起的数据。那么这是属于一个就是当时没有这种想法的。如果是我们把它稍微理想化一点，通过数字模拟可以看得到，在不到360天，也就不到1年的时间，它可以达到甲烷化率87.9%，就是88%。而我们国家中国的国标天然气的含量要求75%以上，所以这个完全没有任何问题。而这个氢气下降很大，而二氧化碳也下降很大。那它是不是 在经济上可行呢，可以肯定知得到，就是经济上一定可行。如果我们具体来说，假设一个气场的原始数量只有1亿方，采储程度40%，工业废气中含氢10%以上，这个是很低的含氢量。生物甲烷化率，比如说我们要求80%，每一年也就每一次利用二氧化碳8810亿吨，单次生化耗时约1年，可再生天然气356万立方米，价值约1000万。那么我们是通过净现值法来计算的，这里面不具体的讲了这些数据。变废为宝的多功能 CCUS 可实现价值可观的正效益。那么它与传统的 CCUS 相比，优势在哪儿呢？主要是在降低了碳捕体难度及成本，因为我们不需要它的纯度，而我们用 CCUS 需要95%以上的纯度，甚至于99%，而大的提升了碳封存效率。同时，变废就是属于不纯的二氧化碳和不纯的氢气，为宝实现碳循环资源化、能源化利用，以及碳循环经济。那么地下它的这个已经开采过的也叫枯竭的油气厂，它就相当于是我们不花钱建造的大型天然生化反应器工厂，这个效率非常的高。那它有多大的发展潜力呢？如果我们把2021年中国，我刚刚已经说过了，所有的这个工业副产气中的氢的含量是2亿立方米，它就可以利用1亿吨二氧化碳，可以合成天然气600亿立方米。这个是个什么概念呢？四川省去年是550亿立方米的天然气产量，是中国所有的内地31个省市最高的产量，而我们去年中国只有刚刚2000亿立方米，四川省550亿，所以这个超过了四川省。如果我们2060年中国每年需要通过人工的负碳技术吸收10亿吨二氧化碳，如果我做个简单的外推法，把10亿吨都拿来用于这个 CCUS， 那可以产6000亿立方米的天然气，这个可远远的不得了。而我们在2060年大概需要8000到9000亿立方米，自己产量4000亿，所以我们是1大半以上需要进口。如果这个技术能够变为现实，那是属于非常这个具有战略意义的一件大事情。所以3060双碳战略目标来说，正收益的 CCUS 为最佳选择。如果我们现在刚刚说的是一个大的一个范围，就看中国的常规天然气厂，不要看那个制米天然气或页岩气，因为它的孔穴度和那个渗透率都太低。那一年单次循环利用大概是可以4.3万亿吨二氧化碳，合成2179亿立方米天然气，储能和其他东西最终促成22.8亿吨的二氧化碳。这是气场。油厂的话，我们首先把石油，就是残余石油降解变成4200亿立方米的甲烷，单次循环利用还有2.26亿吨的二氧化碳，然后生成这个除了这个原油降解生成天然气以外，我们生化合成的还有1100亿立方米的甲烷，最终封成12亿吨二氧化碳。那么我们有这个还是一个方案，是具有挑战性。那挑战主要是4大部分：深层次的机理不清、技术不成熟、复杂的现场选址。我们已经做了很多的研究，但特别是具有挑战的气力管理，因为这些气力源是分布在中国各个地方非常小的地方，它每一个地方的数量很小，怎么的管理法？因此我建议 国家要实行理论研究和技术攻关集中攻关，构建 CCCUS 标准体系，建立 CCCUS 政策支撑体系。最后是一个结论与展望。我们认为变废为宝的多功能才能实现正收益的 CCCUS 有望成为最具发展潜力的全球负碳技术，特别适合于中国和美国。那么 CCUS 与 CCCUS 协同发展至关重要，才应更加关注 CCCUS。也就是说，我们现在这一项技术可以从 CCUS 变为 CCCUS， 也就是 from CCUS to CCCUS。 Thank you for your attention， 谢谢大家，我节约了3分钟。
Okay, thank you very much, Professor Ho, for your introduction of the new CCCUS. And since the time limitation, we go to the next speech. Lithium-bound chemistry drives the high-quality development of energy storage materials by Professor Zhang Qiang from Tsinghua University. Professor Zhang has received numerous accolades, including the National Science Fund for Young Distinguished Young Scholars, the Ministry of Education Young Science Award, the China Young Science and Technology Award, the Beijing Young May 4th Medal, the Newton Advanced Fellowship from the Royal Society, the Liu Bing Award from Tsinghua University, and the Tian Zhao Award at the International Society of Electrochemistry Conference. From 2017 to 2020, he was consecutively recognized as a highly cited researcher globally for 4 years. Professor Zhang has been engaged in research on energy chemistry and energy materials. Recently, he has focused on integrating national strategic needs with fundamental research. His work addresses critical requirements for energy storage and utilization, with an emphasis on the principles of lithium-sulfur batteries and key energy materials. 清华大学的张强教授呢是博士导师，曾获得国家自然科学基金杰出青年基金、英国皇家学会牛顿高级奖学金等多项的奖励。2017到2020年连续4次被评为全球高背景科学家。让我们欢迎张教授做报告。
Thanks, Chairman, for kind introduction. I'm Qiang Zhang from Tsinghua University. It's my great honor to give a talk on this symposium. So I'm very happy to share my recent work on lithium-bound chemistry for advanced energy materials. So you know batteries has been strongly considered worldwide, and we can see a very rising demand for rechargeable battery. If we consider not only the amounts, but also the energy density, we found a high energy density was also goal for our daily life. If we want our car have long drive distance, so the energy density should be as high as possible. You know, most of silicon or graphite anodes can be accepted on lithium-ion battery, but however, their energy density was less than 400 watt-hour per kilogram. So, okay. I found the differences between the slide and the computer. Okay. 两个不一样是吧？ Okay, I found it's working now. So how to build high energy density battery? We found the feasibility of pair different cathodes with a lithium metal anodes was a good choice. The reason was attributed from the bonding energy for lithium. If it's in metal states or lithium ion states, it can give off energy gradually. However, how to control the kinetic process for lithium reduction and oxidation? We found the reaction between the lithium metal to lithium ion. There are a lot of feasible intermediates in lithium sulfur chemistry. For example, once polysulfide was achieved, there are a lot of lithium denoted their electron to sulfide atom. So they prefer to accept electron pairs from printing or prolonic nitrogen. So in this case, not only the charge transfer from lithium to sulfur, there also electron transfer from printing nitrogen to another molecule of polysulfide. So in this case, we call this as lithium bonds. We found the dipole-dipole interaction between two different molecules. So it's another chemical bonding for lithium, not only in metallic or ionic states. It's also lithium bonds between two different molecules. Such phenomenon was also validated by experimental observation. Once NMR characterization was carried out, it is found the upshift to the low field of lithium ions, in which once the printing nitrogen introduced, the peak of lithium to upshift to low fields. So this is quite similar to hydrogen bond formation. And we also clarified the differences between lithium bonds and lithium ions. We found the Coulomb number was dominated. Once the Coulomb number is less than 4, it provides free space to accept electrons from other molecules. So in this case, lithium bonds was achieved. Well, for the case of high Coulomb number of more than 4, they prefer to close packing with each other. So in this case, we can regulate the reaction between different intermediates of lithium-containing compounds. In this case, we propose several catalysts, which can be sulfide, oxide, nitrides. They promote the rapid sulfur redox reaction. We found the appearance of metal can catalyze decomposition of electrolyte. So in this case, metal-free catalyst, in which prolonic nitrogen cluster into prolene rings, in which they accelerate the redox reaction at the metal-free sites. They also accelerate the reaction by lithium bond formation. We validate the lithium bond not only in cathodes. We found the feasibility of lithium bonds with lithium ion with solvents, or once they absorb on the framework of lithium anodes. Let's see what's happened when recently. In this case, they prefer to receive electron and accelerate the reduction of solvents molecule. This induced a lot of gas evolution. The gas was originated from decomposition of the solvents. It's constituted of hydrogen, ethylene, and carbon dioxide. Well, for the case of pure solvents, there is no gas evolution. So the appearance of ion-solvent complex promotes the decomposition of solvents, and it's also not induced not gas but also solid products attached on lithium metal anodes. We found the introduction of carbonates always benefits out of lithium nitride and oxide can be available. So in this case, it provides the feasibility of uniform lithium metal deposition. So from past 50 years, more than thousands of recipes was tried, where few of them can be applied for lithium battery. So it is possible to find which is the favorite for lithium-ion batteries. In this case, we found the trial and error by experiment is very slow. So in this case, we tried accelerate by computer screening by machine learning. In this case, we try to build a single molecule in software, and we get the interaction between different molecules. In this case, we can predict what's happened in solvents, and also once we introduce lithium ion. So in this case, we can get several descriptors of different electrolytes. We can generate the molecule by graph theory in computer very easily. So in this case, we can screen more than tens of thousands very quickly, and we can get that can be predicted. So in this case, we try to cluster our molecule in a finger, in which the red one corresponding to the stable one, while the blue one was unstable, which can be neglected for electrolyte innovation. We are very happy to find the classic molecule always corresponding to the red dot literature. They also corresponding to the stable molecules. And we found that not only space which focused before, there are a lot of opportunity in this area. So this provides very good feasibility for electrolyte screening. We can try which was preferred in working battery. So in this case, it can accelerate the innovation of electrolyte very easily. We also try to validate the role of lithium bonds in the anodes. In anodes, the pure lithium-philic sites by the introduction of lithium bond formation. We found the introduction of oxygen-nitrogen sites. They always prefer strong lithium bonds. In this case, in experimental, we found the introduction of oxygen and nitrogen. They can provide the small reaction barrier and also high-density nucleation. So in this case, it helps the lithium metal deposit in uniform film structure. So in this case, we try to get the composite framework, and we can get the lithium metal anodes in large pieces. It's very helpful to build a battery with energy density of more than 500 watt-hour per kilogram, more than 150 cycles. And once we change the cathode from NCM to lithium-rich magnesium oxide, we found a surprising high energy density of 640 watt-hour per kilogram battery can be achieved. And also, if we full utilization of sulfur, in our case, we can find a battery with more to know what's happened here, and we can design the material easily. And in this case, we are aim to get safe, affordable, and efficient battery system, which is quite necessary for our daily life. And I think the concept of lithium bonds was quite important. Before the end of my talk, I'd like to introduce two journals. One is the Chinese journal, Submission Area. We will accept 700 this year. Another new journal of ES Battery, which was new built by Royal Society in UK. And this is a sister journal of Energy and Environmental Science. 2 years ago, the ES Family Journal of ES Catalysis build received a lot of submission. And also, the batteries and solar was also hot topic. So I'm looking forward to receive your submission soon. I'd like to stop here, and if you have any questions, please write me, and I'd like to answer.
Thanks, Professor Zhang, very much for his time saving. And we can see the machine learning is really work in different fields. And the last presentation will be given by Professor Fei Ding. And the title is Research Status of Quantum Information Technology in Germany, an interpretation based on published data. Professor Fei Ding is mainly engaged in research on semiconductor materials and quantum optical devices, aiming to understand and exploit interesting characteristics of semiconductor nanostructures such as quantum dots, nanomembranes, and emerging 2D materials. He has won the ERC grant, one of the highest honor in Europe. Other awards include Maria Curie Scholar of the European Union, IBM Patent Achievement and Award, IFW Excellence Program, and he was invited to participate in the 70th anniversary of the National Day Parade. The doctoral thesis he supervised won the first place in the Quantum Future Award of the German Ministry of Education and Science. Since 2019, he has also served as the chairman of the Gesellschaft Chemie Physiker in Deutschland, GCPD. Since 2023, he has served as an editorial board member of Light, Science, and Application of Nature magazines. Okay, let's welcome Professor Ding.
Okay, everybody is hungry, so I try to be quick, okay? So, I'm waiting? Yes, okay, good. As you can see, the topic which I'm talking about is quite sensitive, so everything I presented here are collected from public data, yeah, so no one can sue me, yeah? Actually, I would like to briefly introduce my research area, so I think it's more like a joke. Because you see that according to Joe Biden, so United States want to impose a sanction on in China related to quantum technology and semiconductor. But if you visit my group website, you see that we are working on semiconductor nanostructures, and we want to develop novel quantum devices. So basically means that it's nowhere to go for me if I stay in Germany or maybe in United States, okay? So anyway, so talking about quantum technology in Germany, so there's a, let's say, there's a white paper published by BMBF, the German Ministry of Science and Education. So basically in Germany, we will focus on a few areas, just like quantum sensing, quantum computing, and quantum communication. For quantum sensing, there are many interesting applications, such like Earth observation, and also data storage, and also navigation. So both of which are quite important for the whole country, actually. And this is the white paper I mentioned. So it's like a white paper. So the background is that the German government want to or plan to invest 3 billion euros before 2026 on quantum technology. But I am a bit skeptical because of the problem with the German government now, the financial problem. So I hope they keep the promise. Okay. The focus in this white paper is that the government want to support research, let's say from laboratory to field test, and also the white paper want to encourage technology advancement, especially want to build a technology ecosystem for quantum business. Why is there such a program? Because Germany has much lower, let's say, investment on quantum technology compared to China and the United States. So the situation in Germany, there are two things. One is the strengths, what do we have, and also the weakness, what do we have, okay? So I briefly talk about it. For example, in Germany, there's a very long industrial chain. So Germany is an industrial country, everybody knows that, and Germany is a part of the big European market, and we do have many excellent universities, and also there's very high input in fundamental research. For the weakness, this is more like a joke. I think every people who come from Germany will understand the joke. So we have, okay, so this is not a joke, okay, insufficient research on quantum information. This is not a joke, but there's a big joke here. Let's say go to the company, you will find that most of the IT engineers, they are not German. They are from many different countries. Another big problem is the bureaucracy is totally crazy in Germany. But I am happy that the white paper, they acknowledge this problem. But also there are many other problems, just like the students, they typically go to mechanical engineering, electrical engineering, but not so many people study physics today. But okay, if there are also opportunities which bring along by the program. So, for example, there will be a great opportunity for Made in Germany, this slogan. Okay, there will be synergy between industry and users, and also, most interestingly, there can be very exciting new application and also new market brought by SME, the small and medium enterprise. But of course, the challenges are, for example, if you work in the university, you will feel that the lack of technician and also skilled researcher is currently a big problem. And also that very heavy or serious brain drain. So the educated young scientists, typically they go to United States, or many Chinese students, they come back to China. This is the big brain drain problem for the German government. And also they realize that there's a heavy dependence on the non-EU technology. So we know that what is non-EU mean, okay? So but one thing they want to emphasize that there will be potential threat if other country can demonstrate, for example, quantum communication or quantum computing first, and then that could be a security threat, actually. So I try to make the bits for, let's say, between German, English and Chinese, okay? So there are several goals before 2026. So I just point out a few, okay? So because we are really late now. For quantum computing, the white book international also sure, and instead of let's say put the you know, for example, and another picture. So let's say the so-called also. They are so they will so many universities. There are, for example, their additional metrology. And metrology. Atomic clock. And also I knew computer, so they working is for also. The big so a lot to become so Saxon also have also say this is activity you can see project quantum control money so quantum photonic algorithm and year of Hanoi so about around or quantum key distribution. The science and Germany offer. So you can go to the
his last the speakers for they would like to you and go.